Hi everyone who is online. Okay, so you will probably need the materials. You can scan the QR code to get the lesson material for the online students. And then for those physically in class, you should have the revision kit with you. We'll start around 2:05. Okay. Hi. Free sitting. But can I get your name? Junyang. Sing what? Z-A-N-E. Oh, okay. Oh, we will start around 2:05. Oh, sorry. I saw Chloe left the group. I thought it's my class. Chloe left the group. I was like, why is she leaving the group? Okay. Hi. Can I get your names? How do I spell it? Chuen. Chen. R-A-E. Okay. And you are? Nicholas. Hi, the two gentlemen at the back. What's your name? Delvin. Delvin. How do I spell it? Delwin. Okay, and you? Okay, how do I spell? Jervon. Okay, can I just do a quick survey? Which schools are you from? Got Arins tested for EOI? No. Okay. The last two gentlemen. White eye. No Arins, right? Based on what I remembered. Two of you? Alright. Okay, BJ got Arins, RI no Arins. You? SA. Okay, can and then? Okay, got Arins. Can okay, so technically I will be going through organic chem primarily in these 3 hours. When I'm doing the mock paper, that is where I will bring in kinetics and equilibrium. Okay, so primarily the first hour we are looking at organic chem, and then the second and third hour when do mock paper, we will focus more on the soft skills required for kinetics and equilibrium. For those who are in Victoria, based on what I remember, Victoria currently you will be tested Arins in your EOY. However, I do not have time to go through arenes. So what I'm going to cover is the important concept in arenes, which is resonance. Okay. The rest of you can listen to resonance because resonance is perhaps one of the more important concepts around. Okay. Hi, what's your name? Okay, I have a Elise and a Elisa. Correct? Okay. What school are you from? Okay, can. Okay. Okay, so I'm gonna start soon. In fact, I will start now. Okay, give me a minute. Let me just close my door. Okay, let's begin. Okay, quick check for people online. If you have arenes, meaning benzene and alkyl benzene, I will only talk about resonance. I will not talk about the reactions. Okay. Yeah. Okay, let's begin. First thing I need to go through some introductory slides first. Okay. 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 So just hi Joey. Okay. So basically you just call me by my name lah. Don't need to add Mr. or whatsoever. Okay. I'm Ashley. I've been teaching chemistry, mathematics, and physics at secondary school at JC level. Basically I used to be from NTU. After that I worked as a junior editor at Marshall Cavendish. So basically we do textbook publishing. So I edited my pals are here, which is primary school maths, and then I also edited chemistry matters and physics matters, the one that is currently being used right now. Okay. Okay. Just a quick introduction to OVERMUGGED lah. So basically, we have a few branches across Singapore. There is about 1,000 students with us. This year we are trying to expand more in the JC market. So that's that. And then you can find us on Telegram, Instagram, and YouTube. Okay. Technically this session will be recorded. And then if you need any to revise on anything about the crash course, you can always go YouTube and search for it. Okay, just go to the official website. Next, results wise, I think technically most of you should be able to get distinction if you are with us for 2 years. I think there's nothing much for me to say. I think most of you want to just get onto the crash course. So let's get on to that. So today's agenda, the first hour, I'll be going through 3 important concepts that you need for organic chem, which is hybridization, isomerism, as well as reagents and reactivity. After that, we will look at the mock paper itself. So the mock paper I'm going to go through is question 16 and question 18. In question 16, we will discuss about alkanes and we will discuss about free radical. Okay. And then I will bring in the concept of chemical equilibrium. In the third hour or the third part, we will look at question number 18, and that's where we will talk about electrophilic addition as well as chemical kinetics. Okay. Okay, so this is the general overview of what is going to happen today. For people online, if you need the materials, please scan the QR code to access and download the materials. Okay. People in class all have your materials? Okay, good. I'm gonna pass around some blank papers because there will be, you will need to take notes lah. I don't think there's a lot of space left inside the revision kit. Quick, just pass around. Just take 2 to 3 pieces of paper. Joey. Okay. Okay, so what happened is this, primarily as you're going through the crash course today, what should you take away as important soft skills? So we will try to get you to understand the key concepts inside organic chemistry. After that, I will identify certain misconceptions you may have. We will review common questions, and then we will emphasize on the keywords when answering the question. Okay, can I? Okay, so without further ado, I'll start off with the fundamentals that you will need in organic chem. If there's any chapter that is very important for you to review for organic chemistry, is introduction to organic chem. So if your introduction is done well, organic chem becomes relatively easier. But if introduction is done quite badly, you will struggle all the way until next year, May. Because organic chem has about 10 chapters, it will be an 8-month journey long until next year, April or May. Certain schools may drag it until June. That's the last time you will hear of organic chem. Okay. So it takes up about 1/3 of your syllabus actually. Okay, so with that, let's go through organic chem. I'll start off with hybridization first. Hi. No worries. You came at the right time. You're just about to start. Okay, we'll first start off with hybridization. Just a quick show of hands. Who have no idea why you do hybridization? Like, what is the rationale for hybridization? Okay, the rationale is not commonly tested, but I think in order for you to understand why we even do hybridization in the first place, it's important for you to understand the rationale. Okay? Let me look. Oh, okay, sure. Give me a minute. Okay, last call for people who are online who need the QR code to access the materials. It's here. So we're gonna, okay, so take note, rationale for why hybridization occurs in the first place is not tested, but it's good for you to know, just in case they test. Okay, but it's not one of the most commonly tested topics. So, okay, why do we do hybridization in the first place? Is because there's some discrepancy or inadequacy with what you learn in covalent bond formation. So what is that inadequacy? So if you recall, when you form a covalent bond, please don't tell me. Okay, no problem. Okay, so let's go through. So first thing I want to talk about is the rationale. Okay, this thing is recorded. Fantastic. Okay, let's go. Okay, so first thing is rationale. Why do you even do hybridization in the first place? So like what I mentioned, there's some inadequacy with what you learn in covalent bond. So the very basic idea of a covalent bond, if you recall, is that you have one electron, I have one electron, we share that electron, correct? So based on what you learn in covalent bond, if you have one electron, I have one electron, we share, then we'll form a covalent bond. But what is the issue here? So if you look at the ground state configuration of carbon, 1s2, 2s2, 2p2. Focus on the valence. You can technically only form how many bonds? 2. Why? Because you only have 2 unpaired electrons. Correct? The 2s is a paired electron. It cannot be used for covalent bond sharing. So based on this idea, the first problem comes out, which is that carbon can only form 2 bonds. But most of the carbon, in most organic chemistry, the carbon compounds that you have, let's take for example the simplest one, methane, CH4, it can form 4 bonds, correct? So technically the issue in reality, what you see is carbon can form 4 bonds. So this is the reality. This is what the theory is telling you. And the theory is saying something that is not very correct. Next, then we say, okay, never mind. Let's excite the electron. So we look at excited state configuration of your carbon. 1s2, 2s1, 2p3. So now most of you will tell me, hey, there is 4 unpaired electron. I can form 4 bonds now. But are the 4 bonds equivalent? That is the question. Because based on what you observe in methane, the CH bond is all the same. Correct? Number 2, the CH bond length is also the same. Third thing, the CH bond, the bond angle is 109. Correct? Okay. Can? So basically, based on what you observe, based on this theory, yes, you can form 4 bonds, but why is it wrong? Because the carbon can form 4 inequivalent bonds. But technically, what you observe is that carbon should form 4 equivalent bonds. What are the evidence here that shows you that the bonds are equivalent? Number 1, CH bond energy, same. 2, CH bond length, also the same. Now, the third one is a bit hard to visualize, but let me just, you go back and think about it. Based on what you learn in your atomic structure, p orbitals, what is the bond angle with respect to each other? 90 degrees, am I correct? So if you think about your px, py, pz orbital, 1, 2, 3. If really the p orbitals were around and they overlap with a hydrogen, what should the bond angle be? 90 degree. But based on what you learn in methane, methane is 109. Correct? So the bond angle also don't make sense. So the CH bond angle is not equal to 90 degree. All of this mounting evidence tells you that, hey, what you learn in valence bond theory is not 100% accurate. And that is why chemists developed something new called hybridization. Okay? So first thing is to understand the rationale. Why you do hybridization is because your covalent bond, or what we like to call as the valence bond theory, don't make sense. Okay? Valence bond theory means you have 1 electron, I have 1 electron, we share. Dative bond theory is you have 2 electron, I don't have electron, you share with me. Understand? But we are focusing more on the valence bond part. Okay? 1 electron sharing, that sharing has some problems. So because of that problem, they come out with hybridization. So the next part is to get you to understand what is hybridization. Now, in a very simple analogy, you think of hybridization as this. You take the s orbital like an apple. You take the p orbital like a banana. So if you think about it, most atoms will have 1 apple, 3 banana, correct? So in total, how many fruits? 4 fruits. You take these 4 fruits, put it inside the blender, you blend it up, boom, then you pour out. So you pour out how many cups of fruit juice? 4. So it's the same idea here. Basically what you do is, you take 4 atomic orbitals, put it inside your blender, they will blend it up for you, and they will come out 4 hybrid orbitals. Okay, so in terms of exam question, when it comes to hybridization, what are we looking for? Usually 3 very important concepts they will test you lah. Number 1 is, how are the hybrid orbitals formed? Number 2, the diagram to show hybrid orbitals. And number 3, identifying the hybridization of the atom. So I will be tackling these 3 parts today. For the first, at least to cover up hybridization. So as of now, and everyone can understand what hybridization is. It's basically you take your s orbitals and your p orbitals and you mix them together to form hybrid orbitals. Okay? Okay, so let's cover the first question. How are hybrid orbitals formed? So to understand how are hybrid orbitals formed, you need to know what atomic orbitals you use. Correct? To get those hybrid orbitals. Anyone don't have blank paper? Because you probably don't have enough space. Come pass around again. Just take 2 to 3 pieces. Okay, those who just came in, you probably need some extra paper. Okay, so first thing we'll cover how our hybrid orbitals work. Okay, what we need to do is we need to know what atomic orbitals you use. So the key concept is this. Just now what I told you, you put in 4 fruits, it comes out 4 fruit juice, correct? 4 cups of fruit juice. So basically the most important idea is the number of atomic orbitals that you use, meaning what is the number of atomic orbitals you use for your hybridization. It will equate to how much hybrid orbitals you form in the end. Okay, so the number of hybrid atomic orbitals you put inside, or you ask the system to do the hybridization will be equal to the number of hybrid orbitals you form. Okay, so first thing, so very first part, what you need to know is what are the atomic orbitals you use. Now, what atomic orbitals you use is all coded inside the name of the hybridization. What do I mean? So you think about the word sp3. So when you, this is not a very good color. Okay, wait, let's think of sp3. So if you look at sp3, right, basically what happened is you have your s orbital and your p orbital. So this is the type of atomic orbitals you're going to use for your hybridization. Number 2, what is the number? So you look at the power, s to the power of 1. So you use how many s orbitals? 1. P3 means you use 3 p orbitals. Understand? So the number is based on the power. Everything is coded inside the word itself. Meaning that if you're looking at sp2, it will be 1s2p. If you're looking at sp, it's 1s1p. Now, some of you may be asking, can d orbitals do hybridization? Yes. So there are things like what sp2d2 hybridization. Is it in syllabus? No. Will it come out as an application? Unlikely. Because it's too high level. We learned this in like year 3 of uni. So actually technically it's quite hard for them to test you on this. I said, so at most they will go up is sp3 hybrid orbitals only. Even if you go on to take H3 chemistry, unlikely will come out. Okay, so don't need to stress, just need to focus on sp3, sp2, and sp. So you come again. Okay, so you understand the type of orbitals and the type and number of atomic orbitals you use. So you put it inside the blender, blend it up. So you think about it. sp3, how many atomic orbitals you use? 1 plus 3, so 4. So which means that the number of hybrid orbitals that comes out will be 4. Because 1 plus 3 give you 4. So we call these hybrid orbitals the sp3 hybrid orbital. So you think about the rest. 1s, 2p, total 3. Put inside the blender, come out 3 hybrid orbitals. Okay, one S, one P, put it inside the blender, come out 2 sp hybrid orbitals. Next, your next mission is to understand how all these hybrid orbitals arrange themselves. So if you see the diagram here, I have drawn for you the diagram to show how the hybrid orbitals look like. How do you remember? Very simple. Think of them as this. So you think of your hybrid orbital as a bond pair. So if you have 4 hybrid orbital, 4 bond pair based on VSEPR, what shape? Lucas, tetrahedral, correct? Next, if you have 3 hybrid orbitals, take it as 3 bond pair. 顺道 trigonal planar. If you have 2 hybrid orbital, correct? How will they arrange themselves? Nicholas, linear. Understand? So even if, let's say today, really suay lah, they test you sp2d2. First thing is, how many hybrid orbitals do you have? 1s, 2p, 2d, 5. So you put in all these atomic orbital into your blender, come out 5 hybrid orbital. How will they arrange themselves? Trigonal, bipyramidal. You learn year 3 uni stuff already. Good for you. Okay. So basically that's how we do this. Okay. That is part. Sorry, that is part 4 and part 5. Now, there's still something that is quite important. So for certain cases, you didn't use all your atomic orbitals, correct? For example, the sp and the sp2, you didn't really use all your atomic orbitals, correct? So if you think about it, standard, we always have 1s and 3p. So for sp2, what do? You use the 1s and you use out of the 3, 2p orbitals. Okay, maybe I shouldn't write it this way because some of you will think it's your shell orbitals is 1s orbital and 3p orbitals, correct? So out of the, for sp2, out of the 3p orbitals, you use 2. So you're left with how many? 1, correct? So you have 1 hybrid orbital. How would the hybrid orbital look like in terms of real life? So you must remember, unhybridized orbitals are always 90 degrees to the hybrid orbital. Okay, so I think the part that some of you are facing a lot of problems with is that you cannot visualize how the hybrid orbital look like. Okay, so I'm going to stop share first, pin myself so that everyone can see me. Okay, so if you see, this is how the sp2 hybrid orbital will look like. What do I mean? If you see the blue straws, the blue straws are your hybrid orbital. It's your 3 sp2 hybrid orbital. So based on what we know, they arrange themselves in a trigonal planar manner, correct? Sorry, I paste until not like trigonal planar, but it's trigonal planar lah. Because the 3 hybrid orbitals are all lying flat on this piece of paper, correct? So that's why it's called planar. Next, how would the p orbital look like? So the p orbital is the chopstick. It will cut through and is perpendicular to all the hybrid orbitals. So if you can see here, here 90 degree, here 90 degree, here 90 degree. Okay? So this is how the sp2 hybrid orbitals will look like. The straws are your hybrid orbitals. The chopstick is the unhybridized p orbital. So the unhybridized p orbital will always be perpendicular to the hybrid orbitals. Okay, don't destroy my model because I need it later. Here, pass around, take a look. Here we go. Okay, next. This is to really get you to really be able to visualize how your hybrid orbitals look like. Because if not, every time everyone will ask me how the p orbital will look like, where is it supposed to be? It is cutting through the middle of the hybrid orbitals. Okay, can just rotate it this way. Now, if you want to take a photo of how the model looks like, you can go ahead. Because if you see in 2D, it might not be very clear, correct? But if I put it in 3D, it will be better for all of you. Okay, next. We are going to talk about these sp hybrid orbitals. Because this sp hybrid orbital, the visualization is way more difficult. Okay, so everyone ready? Okay, I pin myself again. So technically, what I've done was I've built some kind of model to show you how the hybrid orbital look like. So once again, same thing. The straws is the hybrid orbital, correct? So if you can see, this is one sp hybrid orbital. This is another sp hybrid orbital, correct? Remember, p orbitals are always perpendicular to the hybrid orbital. So one p orbital will be perpendicular this way, 90 degrees. The other p orbital, where can you place it such that it's 90 degrees? Straight as in like that? Yes, you're correct. So the other p orbital looks like this. If you can see, this is also 90 degrees. How? 90 degrees in this manner. I said, next thing, it has to be here. It cannot be anywhere. Because by right, some of you may be thinking, like that is also 90 degrees, correct? But what happens is you must go back to what you learned in atomic orbitals. P orbitals are always 90 degrees to each other. So this p orbital need to be 90 degrees to this set of chopstick as well as to the hybrid orbital. So it can only be in this position like this. So your sp2 hybrid orbital will look something like this. Wait, let me just. So it has to be like this. Okay. Okay, good. Like this. Okay, come. So important idea is, remember, your unhybridized p orbitals is always 90 degrees to your hybrid orbitals. Okay. Here. Okay. It's okay. Thanks. I need this thing. Okay, next. People online, get ready a full scat or some paper, because the next part we're gonna do is we're gonna talk about the diagrams. Now, in most exam questions, they are not gonna ask you to just draw how the hybrid orbital look like for an atom. So instead of drawing the hybrid orbitals for an atom, they're gonna ask you to draw the hybrid orbitals for a molecule. Okay, this is the fifth thing. Okay, but before I get you guys to draw, okay, I think most of you, your problem right now is, you know that there's these three modes of hybridization. So you know that there are these three modes of hybridization. But the issue is you want a quick way to be able to identify the hybrid orbitals, correct? So basically what happened is, what your teacher could probably teach you is to calculate the number of sigma bonds and pi bonds. That is too slow. Okay, and some of you, your sigma and pi, you're still not very clear. Okay, but important thing you need to take note of is this. Hybrid orbitals will only form sigma bonds. Unhybridized orbitals will form pi bonds. So we will illustrate this later when I draw the diagram. What I want you to do now is, or what I want to explain right now is, how do I identify the hybridization immediately? Just looking at the molecule itself, I can immediately identify the hybridization. Don't look at the sigma bonds and pi bonds. Look at whether is it a single bond, double bond, or a triple bond. So technically what happened is, if you are sp3 hybridized, correct? sp3 hybridized based on what? If you go back and look at your notes, it is all sigma bonds. So they will have 4 sigma bonds. But instead of identifying 4 sigma bonds, you just go and look at the atom. Surrounding the atom, all single bonds, sp3. Okay, and this does not just apply to carbon. So carbon will have 4 single bonds. How about oxygen? So oxygen, you will see 2 double bonds. Two single bond. So water, the oxygen is sp2 hybridized. Okay, next. If you recall water have 2 lone pairs, correct? So in terms of the lone pair, where are they? They are actually inside the hybrid orbital. So I'm going to use this as an example. So if you think about the one on the top here, this is oxygen. What happened is it will form one bond, it will form another bond, and then it will have a lone pair here and a lone pair here. So in terms of, for example, water, this is how it looks like. So the lone pairs are kept inside the hybrid orbitals, and the hybrid orbitals are also used for covalent bonding to the hydrogen. Okay, so just go and see if it's all single bonds, sp3. How about nitrogen? So nitrogen, it's gonna look like this. So if you think of ammonia, 1H, 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 then the lone pair on the top like this. So ammonia is the reason why you end up with trigonal pyramidal, correct? And H3. Technically, your teacher should have taught this in chemical bonding. Oh. Okay? So need to remember sp3, single bonds. Next, sp2. sp2, very simple. Just go and find that one double bond. So as long as there's one double bond, it's sp2. Why? Okay, so first thing is need you to understand it. Okay, so carbon, 2 double bond. Oxygen can only do a double bond. So once again, I'm going to explain where the lone pairs are. So you have an oxygen here, double bond. The lone pair will be here. In terms of the diagram, okay, so this is where after you finish this, then I'll use the model to explain to you. So by the way, a double bond is made out of how many sigma and how many pi? 1 sigma, 1 pi, correct? So I'm going to show you where is that sigma bond and the pi bond in a minute. Okay, so everyone capture the mental image here. So imagine look at this image here. The black color ones are your hybrid orbitals. The white color one is your unhybridized p orbital. Okay, so I'm going to show you why is there a double bond right now. Okay, Okay, so if you think of this model, what happened is the yellow color straws are your hybrid orbitals, correct? Your chopstick is the unhybridized p orbital. So technically, where is the double bond? So the double bond is here. You form a sigma bond, and then here and here a pi bond. So for example, something like this. If you think about it this way, the blue and the yellow chopsticks will form a sigma bond. The two chopsticks, the yellow and the blue straws form a sigma bond. The two chopsticks will overlap sideways to form a pi bond. Understand? So this is where you have your double bond. Can see? Understand? Then what happened is here and here hydrogen or other molecules lah. So that is where you form your pi bond. Can see? So head-on overlap, side-on overlap. Okay, give me a minute. So this is the sigma bond. Then here is the pi bond. Okay, can? So basically, if you look back at this diagram, what is going to happen is your oxygen will be able to form a sigma bond here. So imagine this is oxygen, this is another oxygen. It will form a sigma bond here. Then it will form a pi bond because the other oxygen is also sp hybridized, so pi bond. Then lone pair, lone pair. So for those of you who are in class, basically one lone pair here, one lone pair here. OO single bond, OO sigma bond, OO pi bond. So that is how your O2 molecule look like. Okay. Okay. Those in online, basically what I'm saying is this bond here is the OO sigma bond. This is the OO pi bond. Then you have a lone pair, a lone pair, and a lone pair. So this is how O2 molecules actually look like. There is hybridization when you're looking at O2 molecules. Okay. Now, how about nitrogen? So nitrogen, quite simple lah. Basically, nitrogen needs to have a double bond. So if you think about it, it can only form the double bond this way. And then after that, what happens is it will have a band shape and then a lone pair. So instead of going and count all the sigma and pi, just go and find the double bond. Because as long as you are sp2 hybridized, you will have a pi bond. If I ask you for oxygen, you cannot see the sigma bond, it's no use, correct? So if your teacher asks you to identify it through sigma and pi bond, that is primarily because of carbon. But if I change up the example to oxygen, there is no sigma bond because oxygen can only form one sigma and one pi. It can only form two bonds, correct? So you won't be able to identify two more sigma, then you wouldn't know what is the hybridization. Next thing you need to take note of is they will not only ask carbon. The three most common atoms that they love to ask is carbon, nitrogen, and oxygen. So you need to know how to identify the hybridization. Okay, so instead of looking at sigma and pi, look at the double bonds. Okay. For the very last one is more complicated, which is your sp hybridization. Because sp hybridization, technically, there are two ways to identify them. What are the two ways? So your sp hybridization got two ways. Either one triple bond, which is made up of one sigma plus two pi, or you have two double bonds, which is two sigma plus 2 pi. Okay, first thing, I'm going to draw out how the molecules will look like. So if we are talking about a triple bond, carbon can only form maximum 4 bonds. So you'll look like this. Okay. Oxygen maximum can do 2 bonds. So if you force it to do 3 bonds, you need to put a plus charge to it. And nitrogen can only do triple bond, 3 bonds max. So nothing will happen. So this is one scenario. Second scenario, if we are talking about 2 double bonds, carbon can form a 2 double bond. That thing is called a align, which is what you see here. So this is the first member of the align homologous series. Not in syllabus, but they can still test. Next, oxygen cannot do 4 bonds because oxygen maximum can only do 2 bonds. If you do 3, needs to have a positive charge. So why do I say that it cannot do 4 bonds? If you think about it, oxygen got 6 valence electrons, correct? If you do 4 bonds, 4 plus 4, 8. 8 plus a lone pair, 10. What will happen? You are violating the octet structure. Then some of you will argue, but didn't we learn expansion of octet? Expansion of octet is only for who? Period 3 and above. Oxygen is in period 2. So it can only do maximum 8 valence. So cannot. Okay, so oxygen don't have, nitrogen have, but nitrogen, same thing, maximum is 3 bonds. If you decided that nitrogen today want to have 4 bonds, you need to give it a positive charge so that you don't violate the octet structure. Okay, now let's talk about oxygen. Let's talk about how will the pi bond and the sigma bond look like. Okay, so I'm going to use this as an example to show you in real life how does the pi bond look like. Okay, so I'm going to write it aside here. So example we are now going to focus on is propadiene. So propadiene is C double bond CH H. C double bond CH H. Okay, so come. First activity, let's try to identify the hybridization. So here I have 3 carbon, carbon A, carbon B, and carbon C. So based on what I told you, always look at the bonds. If you look at atom A only got 1 double bond. So it's sp2, fantastic job. Next, the other carbon C, also only got a double bond. So it's sp2, very good. Now, how about the middle carbon? sp, because it has 2 double bond. Okay, now this one not difficult. What is difficult is the drawing, and to understand the drawing, you should understand the model. Okay, so once again, I need to pin myself. This time round, hopefully all of you can see. So here I have a sp carbon, correct? This is my sp hybrid orbital. This is my sp hybrid orbital. I have a p orbital in this manner and a p orbital in this manner, correct? So this is the middle carbon. Next, I have a sp2 hybrid orbital carbon. So technically what happened is it will, so this is the middle carbon, this is carbon B, this is carbon C, for example, or carbon A lah. Okay, so if you can see, basically what happened is it forms a sigma bond here, correct? Then the pi bond is this way. Can see, right? Your hydrogen is here. So for those of you who are online, hydrogen here, hydrogen here. Next, if I bring in another sp hybrid orbital, okay, this time around I need, yeah, so it's like that, right? Technically, can I form the hybrid orbital this way? Why can leh? This middle one is already bonded to this one here. So it's already used up. Correct? So for those of you who cannot see, basically what happened is you already have a pi bond in this manner. Correct? So what happened is if you position your third carbon in this manner, there will be a problem. Because the middle carbon, the p orbital, has already been used up, meaning this one here. So what you need to do is you need to rotate your molecule this way such that the p orbital is now formed in this manner. Like that. Okay, so for better visualization, I'm going to stand back. So if you all can see, right, technically the molecule must be in this manner here, like this. Can see, right? Can see how the p orbital work, huh? So Joey, don't mind, you help me grab this part. Grab here. Grab where the yellow and the here. Okay, can. Thanks. Okay, come. I try not to put you in. Okay, so for those of you who can see, right? Oh, where's my white pen? So what happened is there will be one p orbital here, here, and here, this manner, and one p orbital. You don't move. You don't rotate. I rotate myself. Okay, so there's one p orbital here, and then there's one p orbital here. One pi bond in this manner, one pi bond in this manner. So your two pi bonds are technically perpendicular to each other. You can see, right? Thanks. So I show you again. So here and here, one pi bond. Here and here, one pi bond. Okay? Okay, people online. So the two pi bonds are perpendicular to each other. Can see, right? Okay? So actually, technically, what happened is your two extreme ends, the hydrogen, they are perpendicular to each other. Can see? Because the hydrogen is arranged in this manner. Then the hydrogen is arranged flat. So meaning that the molecule, if you can see, I'm going to push it down. The whole molecule by right is flat, except for the two yellow straws at the end. They start to become perpendicular. Okay? Can? Okay, give me a minute. Maybe I go and scotch tape the thing in. Where's my scotch tape? Am I going to... Okay, give me a minute, everyone. Y'all can like take a short break. Yeah, is that toilet or not? You have to go outside. The lift lobby. Oh, lift lobby. Yeah. No idea. Sure, thank you. Yeah. Okay, I'm done. Okay, wait, people online. Okay, so technically I put it here. Okay, so if you can see, right, technically this is how the whole molecule look like for a proper diene. do you see that the masking tape here and here? So this is the pi bond. I said, people online, if you can see, there's a masking tape here and the masking tape. Yeah. And the masking tape, I should be holding it this way. No, I should be holding it this way. And the masking tape here. So these two masking tape shows you the pi bond. Okay? What's come to worst? Damn it. Pi. No, okay. This way. Oh. Can see the word pi? So if you can see, the two pi bonds are perpendicular to each other. Okay? Okay, anyway, later you can come to the front and observe this. Okay? Okay, that's all I need to talk about for hybridization. So the very last part is I'm going to show you how to draw the diagram. Then we can move on to the next part. Okay, now when it comes to diagram drawing, what you need to take note of is, so when it comes to diagram drawing, take note, in the old, if you look at very old papers, meaning pre-2017, the MOE's directive was that they want the pi bond and the sigma bond separated. Okay, but nowadays, they say don't separate them, put them all together. So you have to draw everything together. Okay, so we start off with the easiest, ethene. So ethene basically it's this molecule here. Okay, and there is a double bond there. So first thing is, once you are given a molecule, work out the hybridization first. So what will be the hybridization for these two carbon? You have a double bond in the middle, one double bond, so it's sp2. Okay, so if you recall, sp2 is what? A trigonal planar, correct? With a p orbital. So what you do is take a pencil, sketch out the trigonal planar shape first. Now you don't have to erase away. Why you want to sketch out the rough shape of a trigonal planar is because so that when you draw your big lobe, small lobe, it is not that difficult. So here, then you do big lobe, small lobe, big lobe, small lobe, big lobe, small lobe. Because a hybrid orbital, the shape, one hybrid orbital will look like this. And sp2, you have 3 hybrid orbitals, correct? So the 3 hybrid orbitals will arrange themselves in a trigonal planar manner. So this is for one carbon. Next, you need to do another carbon. So same thing, use your pencil, do the rough sketch first. From there, big lobe, small lobe, big lobe, small lobe, big lobe, small lobe. This is your carbon, the other carbon. Now, both carbon has an unhybridized p orbital. Okay, so for the sake of getting you to understand, I'm going to do a different color, correct? But during exam, you can only use one color, which is either black or blue. Okay? So it has a p orbital that is unhybridized looking like this. It has a p orbital that is unhybridized looking like this. Correct? So the two p orbitals will overlap with each other in this manner. So this is primarily how your CC double bond will look like. Okay? Now, you draw this. You never give me any label. No lah. I give you only 1 mark out of 2 marks. No, no. Some teacher very strict will be 0 mark out of 2 mark. You never label for them is straight away immediate 0. So you must always label. So what do you label? So in a pi bond, in a double bond, there is a sigma bond and a pi bond. Am I correct? So you must label the one in the middle here, the CC sigma bond. And then what happened is, here you label it CC pi bond. Now they're going to ask you to draw the whole molecule out. So don't forget your hydrogens, okay? And in fact, I draw wrongly ethene because ethene is C2H4, not C3, not C2H6. So this is how ethene looks like. So 2 hydrogen, change color. For 2 hydrogen on each carbon. So next, don't forget, you still must label CH sigma bond. So this is the full diagram of how your ethene should look like. This one will be worth 3 marks. Yeah. It'll be worth 3 marks. You go and see exam prelim questions, usually is 3 marks. Easiest 3 mark, not the hardest 3 mark. Don't cry. I never even asked you to draw proper diene, no? So they might ask you to draw proper diene. How proper diene. Okay, give me a minute. I'll show you guys. Okay, this is how you draw proper diene. So if you want, you can take a screenshot. Okay, wait. So proper diene is the one on the top that we just went through here. So I show you the model, but how do you translate the model into diagram? So it will look something like this. For those in class, you can take a photo of the screen. Those online, you can take a screenshot. Hey, actually, if you all don't mind, give me a minute. I'm gonna color code it. So give me a minute. I think I will color code it. Okay, what do I mean by color code it? Give me a minute. I'll still share. Don't worry. Hey, wait, someone asked me to move up something, right? Oh, sure. Hey, sorry, AG, which part are you talking about? I totally miss you. Oh, you mean the diagram? Okay, give me a minute. I'll go back to the diagram in a minute. So this one, you'll just need to screenshot. I just need to label the other unhybridized p orbital in a different color because it's looking like black. I don't think anyone can differentiate it. Okay, so I'm going to use blue and give a thick one. Yeah, not thick enough. So you can see the 2 red color orbitals. The 2 red color p orbitals will form 1 pi bond, and then the 2 blue color p orbitals will form the second pi bond. So usually what I will do is this. I will use my pencil and sketch out a plane. So I'll sketch out this plane and then I'll sketch out the vertical plane. So meaning the 2 planes should look like this. One looking flat like this and then one doing this. Okay, then you direct all of them to the corners of the plane, like what I draw here. So if you see, the p orbitals are directed to the corner of the plane. Meaning that when I draw, right, after I sketch out the dotted line, then what I'll do is I will draw it this way, such that it touches here and it touches here. Then your diagram wouldn't look weird already. Okay. Okay, so this one, everyone just screenshot lah. I don't have time for you to draw. Yeah. Plain lines are not, but plain lines is to aid you in drawing. Then don't need to erase away. Don't need to. Some people will erase away lah, but actually technically don't need because they don't mark pencil lines. So you must remember when you do your paper, everything must be in pen, even the drawing. Yes, if your drawing not in pen, your teacher might mark you wrong or not mark it at all. No, drawings all in pen. The part about rationale. Okay, give me a minute. Yes, drawing must be in pen. The only thing I allow pencil is when you do your practical, you draw table or graph. These two must be in pencil. The rest all in pen. Huh? Yeah, lor. But you draw in pencil outline, you waste time. So you must be very fast. You think about it, you all got time to finish paper, man. All your WAs, all always no time on one, right? Okay. Okay, so going back, some of you need this part. Okay, we are done with hybridization. Anyone got any problems with hybridization? Okay, people online, if you are good with hybridization, give me a thumbs up. Give me a minute. Yes, now. So that I know you are good, I can move on. Okay, second biggest problem that most of you have next is isomerism. But specifically, I don't think all of you have problems with structural. It's the stereoisomerism that you have more problems with. Okay? So anyone have problems with structural isomerism? Structural meaning chain, positional, and functional group. Okay, later I'll share with you the exam strategy, meaning that if I give you a formula, how do you derive out all the structural formula and all the stereo isomers? But let me go through stereo first, because I think most of you have problems with stereo. So the next thing we're going to look at is stereo isomerism. Okay, share with you guys. So first thing, this is a flow chart for you to understand the 5 different types of isomerism that you will encounter for your in the A-level syllabus. Okay, so we are talking about structural isomerism. So structural isomerism, basically the idea is the molecular formula is the same, but the way you connect your atoms are different. So different structural formula basically means different connections. The atoms are connected differently. Or we can say it's different sequential arrangement. So sometimes the carbon, sometimes the chlorine is attached to the first carbon. Sometimes the chlorine is attached to the last carbon. Okay, wait, Ray. Just curious, how to identify the number of isomers immediately from the formula? Is it possible? It's not possible. You have to slowly think. There is a method of thinking. So it's not like I give you the formula, you straight away like, you know, can in Chinese they call it tong ling, and then you can like get the number. No, no such thing. You have to slowly work it out. But there is a, how should I say, order of thinking that I'm going to do at the very end before I move on to the next section. Okay, so let me clear up what is stereoisomers first. Okay, next thing about stereoisomers is that they have the same molecular formula, they have the same structural formula, meaning that the way they are being connected, the atoms that is being connected is all the same. However, what happened is very weird. In terms of three-dimensional, it looks different. Example I can give you in terms of what is three-dimensional that looks different is you and your mirror image. Yes. So you look at yourself and your mirror image. Can you overlap? No. Same thing. So it goes for, it's also the same thing for cis trans. Is that you take the cis isomer, you overlap it with the trans isomer, they are never the same. I said, just like how my left hand, if I try to overlap with my right hand, if I overlap the thumb, my fingers cannot overlap. I overlap with the index finger, my other fingers cannot overlap, correct? So these two can never overlap with each other. I said, so that is what we mean by stereoisomerism, different 3D structures. Okay, now for these two, so technically there's cis-trans isomerism and enantiomerism. When I talk about enantiomerism, I'm going to share with you a third kind. The third kind is called configurational isomerism. Because A-level is a very irritating examining body. They always say they don't want to test this, but they always end up going and test this. Meaning that you go and look at your question 13. That is what we are talking about. So in enantiomerism, it's important for all of you to actually understand this thing called configurational isomerism. If you are interested to take H3, you will learn about configurational isomerism. It's not a difficult thing to understand. Okay? Okay, so we'll first settle cis-trans. Okay, when it comes to stereoisomerism, right? Basically, what you need to understand is the conditions. I said, you just need to remember the conditions. And if you remember the conditions, then it's very easy to do cis-trans already. And if you do understand the conditions, it's very easy to do enantiomerism. So first thing, cis-trans isomerism. You must know what is it meant for. Is it meant for all molecules? The answer is no. It's meant for only two kinds of structure, a CC double bond and a ring structure. So basically, you will only find cis-trans isomerism in alkenes and in ring in cyclic rings. Okay. So why is there cis-trans isomerism? The first condition is the whole idea of restricted rotation. Okay, what is restricted rotation? People online just look at your screen lah. So to better get all of you to understand this, I'm going to show you real life models. Okay. Okay, so what do I mean by restricted rotation? Okay. Okay, and okay. Come. First thing, what do I mean by rotation? Unrestricted rotation. So if technically we are talking about ethane, for example, we have a ethane molecule here. Okay, where is my upper? Why is it not so? No, it should not freeze. I tried this earlier. Okay, everyone, I'm back. Okay, wait. Please work. I want to keep using my own phone. Okay, great. Okay. Okay, sorry, there was a connection issue. Okay. So nothing should happen, but I'm going to rotate everything properly. Hey, just listen to my voice. Okay, so basically I was trying to explain to you guys what restricted rotation means. So if you see this molecule, this is the black atom is a carbon, okay? Let me just no video. Yeah. So if you see, right, this is a carbon, this is a carbon. If there was no pi bond, the sigma bond is not inflexible, meaning that it's like a piece of towel. You can actually squeeze and rotate the towel. So technically what happens is this sigma bond can actually cause this molecule to rotate. So in normal circumstances, your molecules will keep rotating. Understand? You think of it as, you know, after you shower, right? Your towel very wet, what will you do? You will squeeze it, right? It's something similar. So the bond can be rotated. Now the issue is, in an alkene formation, you have a pi bond now. So if you want to rotate the sigma bond, for example, this is the sigma bond, you want to rotate it. It's not rotatable, correct? Because if you want to rotate it, you have to break the pi bond. Break the pi bond, rotate, then form back. And that will take too much energy, correct? So what happens is the pi bond causes the thing to be locked in a configuration like this. Okay, next, if you look at your second condition, the second condition is that each carbon must have two different substituents. That is the second condition. So what happened is, if you look here, two different substituents on this carbon, two different substituents on this carbon. This will allow you to have cis trans Y. So I built the other molecule whereby, okay, we assume this is cis, this is trans. The difference between the two is that one of the side you swap it. So for example, if you see I swap this side, they come here. Now I'm going to show you why they cannot overlap. Because if I try to match the yellow color and the white color together, I overlap this part, what will happen here? Different. They cannot overlap. Now you say, maybe you're playing trick with me. So what I'll do is I flip it, I rotate it. You can see that now this part cannot be rotated, cannot be overlapped. Then why do you need two different substituents? So let's say if they have the same substituent. So now I'm going to change the yellow ball into a white ball. What you're going to see is they can start to overlap already. So meaning that if you see like this, even if let's say I start off with like this, right? I can rotate, overlap. So if it's overlappable, meaning superimposable, then it's not a stereoisomer. So this is the reason why each carbon must have two different substituents. Okay? Okay? Because if you have one carbon with the same substituents, they can overlap with each other. Next, some of you, your teacher explained to you about ring structures, correct? So we're going to see why ring structures have cis trans. Okay, ring structure, I need. Okay, so take note, when I talk about this ring structure, right, I am talking about I'm talking about I'm not talking about benzene. So for those of you who are learning benzene, I'm not talking about benzene here. So I'm talking about a cyclic structure. That means a normal ring structure. Okay, so I have a 5-membered ring here. Okay, our focus is going to be on we are going to focus on these 2 carbons itself. So take note, cis trans does not just apply to alkenes, it can apply to ring structures. So where is the cis, where is the trans? I'm going to make things easier, so I'm not going to be too fancy with the balls. I'm going to give you okay, here. 1. Sorry, I need to change the yellow. So first thing first, you must always remember, cis trans got 2 conditions, correct? First one is restricted rotation. So let me show you why a ring structure has restricted rotation. So if you see, this is the ring structure, right? If you want to rotate it, it's unable to do so. Because it's not, you have to break the bond in order to rotate. So for example, if like, let's say here, I just want to rotate this, I can't, because I'm being locked in a ring. So a ring structure have restricted rotation. Next thing, where is the cis trans? So if you have 2 of the same group pointing up or pointing down, that is the cis isomer. And then if you have them in opposite sides, that's the trans isomer. So why are these 2 not superimposable? So if you see, I try to match the yellow with the white. The other side will not be the same. Even if, let's say today I flip it, it's very hard. You see, I can't even flip it to match this part. So this is why ring structures also have cis trans. I said, okay. So technically, what happened is, yeah, that is why you have cis trans isomerism. So for cis trans isomerism, need to take note. Number 1, there must be restricted rotation. What type of bonds have restricted rotation? Normally, it's your multi-bond, meaning your CC double bond or your CC triple bond, okay? Or your cyclic ring structures. Next thing is you need to check each carbon inside the multi-bond or each carbon inside the ring structure must have two different substituents. Now, some of you, you are being trained to think of cis-trans only in this manner that you see here. Correct? Meaning that you must have same groups on the same side and same groups on different sides. But what happened is in the A-level syllabus, they can expand this idea. How? I can give you 4 different groups, meaning I have something like this. And then what happens is when I draw my isomer, I just need to flip one side. So take note, when you draw the other partner, flip just one side. Don't flip both. You flip both, you're just going back to the same molecule. Now, who is the cis and who is the trans? So here, there's also cis-trans. But how do you determine? Because now none of them look the same. So you must always remember, look at whether is it heavier or lighter. Cis isomers usually is heavier substance. Trans isomer is heavier substance on different sides. So what do I mean? Okay, let's focus on this carbon first. This carbon between Cl and CH3, whose molecular mass is larger? Cl. On the other side, so this is carbon A. Next, carbon B, between ethyl and bromine, who has a larger molecular mass? So need to check, right? Br is 79, roughly around there. C2H5 is 12 plus 12 plus 5, 24, 29. You do this long enough, you can memorize. 29. So Br, heavier. This is the trans isomer. Because if you see the other side, the 2Cl, the heavier groups are on the same side. So that is cis. Now, if you do obviously higher level chem, they will call it what EZ lah, but actually A levels they call it cis trans. So even this also have cis and trans. Okay. Next, what is important about cis trans in terms of physical property? So you must always remember, for a cis isomer, your dipole can never get cancelled out. Why? Okay, so we look at a very simple cis trans, okay? So let me give you this example. So this is the cis isomer. This is the trans isomer. Okay. Who still having problems with dipole? Chemical bonding. Don't be shy. Oh, sorry. Okay, I think some of you still having problem with your bonding, given that my own student WA3 still cannot decipher between polar and non-polar. Okay. So when you want to decipher whether a molecule is polar and non-polar, look at 2 things. First thing, is the bond polar or non-polar? So here you should be able to identify a polar bond, CCl. Now this is the reason why if your teacher tells you that a polar bond only consists of O and F, your teacher is a bit beautifying things too simple. Understand? Because technically, as long as the bond is made up of 2 different atoms, then the bond is considered as polar. The only situation whereby the bond is non-polar is whereby you have the same atoms. So as long as you have 2 different atoms, the bond is considered as polar. But whether that polar bond is significant or not, that is a second issue. Understand? So obviously, those that's attached to O and F, that dipole is very significant. those that is not attached to O and F, the dipole not so significant, but it's still there. So if you think about it, so we identified the polar bonds. So even the CH also have a pole, it's also a polar bond, but it's not significant enough. Correct? But the CCl is a polar bond and is significant enough. So general rule of thumb, how do you know whether the bond is significant or not? In your periodic table, you think of the 7. What is the 7? Meaning, if you look at your periodic table, the bond actually is considered polar if it is NOF and then go down Cl, Br, and I. Usually in general, this is what we are looking at. Then sometimes they might consider phosphorus and sulfur as well. So usually this few, if you have these few atoms inside your bond, the bond should be considered as relatively polar, correct? But who is the top level? NOF. Okay, then Cl, Br, and I, second level, last level, P and S. So usually these few atoms, if you have the bond there, is considered as quite polar. Okay, NOF confirm one, guarantee chop. So coming back here in upper, no, not here, here. Okay, so after you consider whether the bond is polar or not, you have to consider the shape of the molecule. Whether that the shape of the molecule can cancel out the bond, can cancel out the polar bond or not, or can cancel the dipole or not. Hi, sorry people, I'm back. Okay, so whether that shape is polar or not. Oh no, sorry, not the shape is polar or not. Whether the shape can cause the dipole to cancel out. So it's playing tug of war. If you think about it, here you have a dipole going down. Here you have a dipole going down. So it's like you are drowning and then someone is pulling you down. Correct? So if you think of forces, there is a force going down. So there is a overall there's a force pulling you down. So this molecule is polar. Correct? Whereas the one at the side here, these two will cancel each other out. Because one is pulling you downwards to your left, one is pulling you upwards to your right. Correct? So the two pulling forces will cancel each other out. So this one, non-polar. Now you need to understand this. In general, cis will always be polar. Correct? Because cis heavier atoms, usually they are quite strongly they are quite electronegative. So they will pull the molecule downwards. So cis will always have a net dipole moment. It's guaranteed. So they always have net dipole moment, which means that they are always polar. But for trans, they can be polar, they can be non-polar, depending on the bond itself. For example, if today I change the Cl to a F, what is going to happen is the dipole is going to be much greater. Then the two dipoles will not cancel each other out. Correct? So trans can be non-polar, it can also be polar. It really depends on the molecule. But cis, we figure out, is always going to be polar. Next thing, even if let's say we argue that, okay, both are polar, right? But you're going to realize that cis, the dipoles always reinforce each other. But trans, the dipole always cancel each other out. So even if your trans is a polar molecule, the net dipole moment is still not as strong as the cis. So in conclusion, what are we trying to say here? Number one, cis is always polar, trans is polar, non-polar, depending on the molecule. Okay? If both cis, so this is conclusion one. Conclusion two, if cis and trans are both polar, the dipole moment in cis is always going to be greater than the dipole moment in trans. Which means that cis will always be more polar than trans. Okay? So I think I've written it down there. Different physical properties, cis always have a stronger net dipole moment than trans. Okay, we will take a 5 minutes break from here. Come back, we'll look at enantiomerism, and then I'll start with structure question 16. Okay? Yes. Yeah, PD. Yeah, it could be PD versus ID. Yeah, but you should put it as PD. Yeah. Okay, if you have any question during this 5 minutes interim, please sound off. Yes. Yeah. Hey, wait. Oxygen, you think of it this way. Yeah. Not very cool, man. Okay. Yeah. I'm gonna destroy this. Taylor, you okay not? Or are you dying already? Okay. So technically it's lone pair here, lone pair here. You're talking about O2, right?
Yeah.
So O2 is OO double bond.
Yeah.
Okay. So sigma bond, pi bond.
Yeah.
This is the OO double bond. Then there is a lone pair and a lone pair.
Are these like hybridized?
Hybridized. So you can put lone pairs inside hybridized orbitals.
But then for carbon, right?
Yeah. Carbon no lone pairs. What? Carbon 4 electron.
Wait, so carbon like that, then
1 electron.
so it's all in front here like that, right? Then
Yeah.
it becomes
No, but this one, so one is hybridized, the 4 electron is distributed equally into each.
then
Oxygen is 6 electrons, right?
Yeah.
You have to distribute the 6 into the 4.
like, oh, like,
So you think about it, lor. 6, right? Distribute the 4, single. One pair.
yeah.
So you have a pair, you can form bond, man.
Oh,
Then you have to put it in the hybrid orbital.
So
You have to put it in the hybrid orbital.
these four, like,
Yeah.
pair, and
Single, pair.
Then the pair.
Because you are taking 6 electrons and distributing it to
Yeah.
4 hybrid orbitals, correct? So it's a pair, a single and a single. So you can only form 2 bonds.
But then this and this
Yeah.
form hybridized orbitals.
Yeah, you're talking about sp3, right?
I don't know.
If you're talking about sp3, then it will be pair, 2 bonds. If you're talking about sp2, it's still pair, one in the hybrid, one in the unhybridized.
But then,
That means you have a lone pair here, you have a lone pair here. 1 electron. So you can form the whole thing is one. No? The whole p orbital is considered as one.
but then how come oxygen are like sp3 and sp2?
Because it depends on what molecule form. It can form single bond, it can form double bond. If you form double bond, it will be in sp2 format.
Oh,
If it's sp3, it is single bond strong.
oh, then
Can
so SP2 then you got like three hybridized.
okay. Okay, wait, should I lower the aircon? I can. Wait, people online, let me address your issue in a minute. Too far away. Wait, is Jacinta outside? Sorry. Yeah. Oh, I see my signal. Sorry, I see from where. No one, there is fine. Okay, come. 4 questions. Let's go. Okay. Okay, wait, let me just address one by one. Javen, give me a minute, huh? Okay, when I go through enantiomerism, then I will explain what you need to include. Next, under chain isomerism part, do we need to know how to draw the lines? Yes, you need to know how to draw skeletal structures. Okay? Yeah. Wait, let me just reply Javen. Enantiomerism in a minute. Yes, need to know how to draw the lines. Okay, next. Okay. Okay, so online students will only have the revision booklet plus the mock paper. What you're talking about is the revision kit. That one needs to be physical copy. I think what you can do is go and talk to the administrative people, or if not, you wait for me at the end of the class, come and find me again. Okay? That's for, and yeah. Okay, lastly, Cherwin, hi, just want to ask us, cis is only polar if it's attached to NOFPF. No, cis is always polar, be it whether what is attached to. Because what happened with the issue with cis is that you can attach to non-electronegative atoms, but there will always be something pulling it downwards. Unless we are talking about it being purely just carbon and hydrogen, then yeah, you're correct. Okay, I will take some time to explain to Cherwin again. Okay, everyone back, right? I think I'm missing one person. Okay. Okay, I need to do a little bit of small correction. So cis is always polar. That one you need to change it. Cis is mostly polar, except if the thing is a hydrocarbon.
But actually, do you even consider that as cis if it's all?
Because you technically can like that. I can have a methyl group and an ethyl group. So if I have all carbons, that means it's a pure hydrogen carbon. then usually this will be non-polar. Yeah. Thanks, Sherwin. So take note, cis is mostly polar, except if it's in a except if it's a hydrocarbon, then it's usually non-polar. Because there is no polar bonds, or the polar bonds become very insignificant for it to be considered as a polar molecule. Okay, next. Let me talk about enantiomerism. Okay, so same thing as same thing as cis trans. We need to know what are the conditions for enantiomerism. To answer, wait, someone just now was asking me a question. Give me a minute. Okay, Javen, yes. Okay, so what happened is usually they will not ask you to explain the conditions. You will need to know the conditions, and based on the conditions, choose the molecule or identify the chiral carbons. Understand? So technically, do you need to put it inside your answering technique? If they ask you for the conditions, yes. If they didn't ask, no. Okay, so what are the conditions for enantiomerism? So the first condition is you need a chiral carbon with 4 different substituents. So what happens is, as long as you have a carbon with 4 different groups, then it's considered as a chiral carbon. Okay? Next, second condition. There must be an absence of an internal plane of symmetry. So what is this internal plane of symmetry thing? So I'm going to show you guys what I mean first in terms of a diagram. Then I'm going to show you the model. Okay, so the best example to show you internal plane of symmetry is this molecule. Hey, wait, I shouldn't put. So does this molecule have an internal plane of symmetry? Yes. The internal plane of symmetry is here. For some of you who cannot see this internal plane of symmetry, I'm going to now show you. Okay, so imagine the hydrogen is the white ball, the OH is the yellow ball, and then what happened is the COH is the purple ball. Okay, give me a minute. People online, I apologize. Okay, so here, if you see this molecule, okay, now if you see this molecule, what happened is, let's first figure out whether it fulfills condition 1. It does. Because if you focus on this carbon, it has 1, 2, 3, and this whole thing as 4. So it has 4 different substituents. But the issue is that if you were to put a mirror here, correct, you will see that they are mirror image of each other. Correct? Or basically, if you put a plane here, a piece of paper here, correct? they are symmetrical to each other. Correct? So that is what we mean by internal plane of symmetry. Okay, remember just now I say I will teach you what is configurational. Okay, so I'm going to now explain a little bit of configurational. But before that, let me show you why enantiomers are considered as stereoisomers first. Okay, so let me explain why enantiomers are stereoisomers. So here what we are looking at is when you have a carbon with 4 different groups. Let's call them A, B, C, and D, and you put a mirror in between them. The mirror image is looking like this. And you're going to figure out that the mirror image actually cannot overlap with the original molecule. So first thing is, let me show you this part. Okay? So why are they not superimposable? As what we like to call it. Okay. So basically, I'm going to make it simpler. Let me take this out. Let me put a green ball in. So here, I have a molecule looking like this. I'm going to now fix up the mirror image. So the mirror image looks like this, correct? So if you imagine I put a mirror here, these two are mirror images of each other, correct? But why are they not superimposable? Meaning that if I try to match the white color and the yellow color together, I overlap it. Do you see that the green and the purple cannot match? Correct? Now, so in terms of 3D structure is that one carbon attached to exactly the same type of atoms. A white ball, a yellow ball, a purple ball, and a green ball. But what happens is when you try to overlap them, they cannot overlap with each other. Right? Then some of you will say, okay, let's try to match these two together. So these two, if you match it together, then the white and the yellow becomes not superimposable. Okay? So this is what we mean by enantiomerism. Basically, in enantiomerism, they are just mirror images of each other. Okay, who here take physics? So when you learn physics, superimposable is superposition, correct? Right? No, actually the chapter before that, wave motion, correct? You learn about polarization. Okay, so for those of you who don't take physics, don't worry. What is polarization? Yeah. If you want, you can take a photo of this. For those of you who don't, oh wait, why is it still this? Okay, never mind. I'll use that like that. Now, so basically what happened is in physics, right? We learned that in order to produce a light, there is many planes to produce the light. So it will look something like here. This is called the unpolarized light. But if you pull it through a polarizer, then what happens is that it will only select one plane. When you put that plane through a mirror, through one enantiomer, it will rotate the light. I said. So basically, if you think about it, I'm going to now pin myself. Okay, so what am I saying? Is that if let's say today you imagine my Apple Pencil is the light shining towards you, correct? to produce this white color light, I have many planes. The planes being, it could be here, like this, or it could be here, like this. In fact, this plane can also produce, so the whole thing is like 360 degrees. But what happens is when you put it through a polarizer, it will only select one plane. So let's say it selected this plane. If you put it through only one mirror image, not two, that means if you think about it, when you have a enantiomer, you will have two mirror image, correct? You put it through one of the mirror image, it will rotate the light here. So when you detect it this way. Understand? So that is called optical activity. But if let's say you put it through a mixture of two enantiomer, what will happen? The A enantiomer, A mirror image will rotate the light this way, then B will rotate it back. So when you detect the light, originally you detect it this way, one rotate back, you detect nothing. So no optical activity. Now, if you think about it, if the two mirror images are in different amounts, mirror image A will rotate it this way, mirror image B will rotate it backwards, but it cannot rotate it back fully. So there is a deviation, that deviation is your optical activity. Understand? For bio students, technically, if you don't know what is plane polarized light, never mind. You just imagine it as, this is the light, there is a paper on top of the light, like what I'm showing you right now. Then you imagine this paper rotating it clockwise and anti-clockwise. So what happens is when you have a pair of enantiomer, one will rotate it clockwise, one will rotate it anti-clockwise. If they are in equal amount, then the clockwise and the anti-clockwise rotation will cancel each other out. Right? If they are not in equal amount, being that there is only one mirror image, or the two mirror images are present but in not the exact amount, then there will be optical activity. Okay? So here, I think this part very important.
Think of it like refraction like that. Just direct the line to a different.
Think of it more like
Like
good twin, bad twin. Good twin, turn it this way, bad twin want to turn it back. If the good twin is stronger in strength, will rotate it more. Then the bad twin, not so good, will rotate only slightly backwards. Understand? Apa? Sorry, people online, give me a minute. Let me show you what I mean. Okay, so what I'm trying to say is this part quite important. Optical activity is observed if only one of the two, that means only one mirror image is observed. If you have a racemic mixture, what is this word racemic? A racemic basically means equal amount. So usually if let's say you have enantiomers in equal amount, we call the mixture racemic law. So then that one, the light will keep rotating backwards. Rotating, one rotated here, then the other one will rotate it back. Okay, so very simple. Just think of it this way. If you have mirror image A, it will rotate the light here, become like that. If you have mirror image B, the enantiomer will rotate the light here. If you have both in equal amount, what happens is one will rotate it this way, then the other one will rotate it backwards. So here got optical activity. Here no optical activity. Yes, they cancel each other out. Optical activity means I must detect a deviation. If I don't detect a deviation, it's not called optical activity. Okay. That one you can attach it any way you want it to be. But usually when you draw, you attach the longer one to the solid lines. So usually if I have a very weird molecule, I will try to attach the bigger groups on the solid lines. Then the wedge and dash, usually I put very small atoms like hydrogen OH. Because when you draw the mirror image, it's easier. So for example, if let's say I have something like this, okay? I have a COH, I have a C2H5, I have a H, and I have a CH3. What I usually would like to do is, this two is bigger, more complicated. Usually I put them as the solid lines. Then the bow lines, I put the smaller groups, like things like this. Then it's easier to draw, so that when you draw the mirror image, your COH is still in the same direction like this. Then your CH3, you do it this way. Then the C2H5, you can write it in the same direction. Okay, I tell you why this is it. Why you should do it this way. Because last time, my time, that means when I take A levels, right? We are allowed to write the thing backwards, meaning that I am allowed to write it this way. The teacher can understand. I don't know why nowadays the teacher cannot understand. So the teacher will prefer you to write it from left to right. So which means that all of you need to write it in this manner now. Because I think the teacher cannot read or something. And then last time the older teacher can read lah, so they don't mind it backwards. I said, so actually technically, take note, all of the small groups, you must write it from left to right. So if you see the CH3 here, right? I never really write it in the reverse direction. I try to write it from left to right. So this is the part whereby they can deduct you marks. Why? Because if you anyhow point, meaning that you draw something like this, I'll mark you wrong. Because the carbon is not attached to the H. The carbon is attached to the C. So I think if you did O levels or you did your IP Chem, your teacher will be very anal about you drawing structures. You must point to the correct atom. Because if you point it anywhere you want, the teacher can circle it and don't give you any marks. Understand? If you take a recent WA involving organic chem, then this is likely what happen. So if you see, I'm very particular. I must point it correctly to this C. So that is the not so good thing about drawing it from left to right. Okay, now back to what I wanted to say. So got 1 year something came up, okay, which was involving this molecule. So what they told the student was they had this structure, meaning the formula was CHOH-CO. That means they give them this formula. Okay? Then they told the student there is one that has no optical activity. There is one whereby you observe optical activity in the clockwise manner. And there is one whereby you observe optical activity in the anti-clockwise manner. So just now we already established that this molecule have a internal plane of symmetry. How did the molecule still have optical activity? And that is where you need to think of something called configurational isomerism. So what is configurational isomerism? I already told you about it actually. Remember just now we were talking about restricted rotation, correct? And then I told you that what's the opposite of restricted rotation? Free rotation. So when you have free rotation, you will have configurational isomerism. Okay, so let me show you. No. Okay, so just now we were saying, right, this molecule here, okay, so we are saying that this molecule has an internal plane of symmetry. So by right, not supposed to have optical activity, correct? But what happened is you need to consider something called configurational isomerism. So ultimately, what is configurational isomerism? So take a look. Now, configurational isomerism basically means that the molecules can rotate. So I want you to see the molecule in this manner, okay? So you all see the molecule in this manner. Okay, bearing in mind this is the bond that will rotate. So what happens is this is one configuration. When the bond starts to rotate, another configuration. Rotate another 30 degrees, third configuration. Fourth, fifth, sixth, back. So every rotation itself, you will have a new isomer. This is what we call configurational isomerism. So what happened is, yes, this molecule originally have a plane of symmetry. If it looks like this, obviously there's no optical activity. What if I rotate it this way? Is there still an internal plane of symmetry? No. So then what happens is this will have optical activity. And the mirror image, the yellow and the purple one is the green one and the purple one is the same. And the mirror image will be able to rotate another light. So this one will rotate the light clockwise, this one will rotate the light anti-clockwise. I think?
Actually, just asking out.
Yes.
Do you need energy to rotate it? Like,
yes, correct.
Change configuration.
So that's why you need energy to rotate it, which is why there's configurational isomers.
Naturally rotate it.
It will naturally rotate, but if you think about it, when you are in this configuration, right, the molecules are all very close to each other, correct?
Yeah.
So there's a lot of energy.
Okay.
But if you rotate it this way, they will not, because there's now this space here that can accommodate the electronic repulsion here. So this one is a better configuration. So actually for configurational isomerism, the energy will look like a sine graph. It will keep going up, coming down, going up, coming down. Because the moment you are in this configuration, it is low energy. But the moment you are in this configuration, it's high energy.
And does it rotate by only 60 degrees or 30 degrees?
Ideally, it can rotate any degree, but usually we will only consider 30. Because there's 6 sectors. 1, 2, 3, 4, 5, 6. Okay. So configurational isomerism is not tested. But what happened is it is tested subtly. How? You all take a look at the MCQ of your mock paper question 13. Anyway, by the way, FYI, question 13 is an A-level question. So which molecule can rotate plane polarized light? How do I know which atoms to draw the wedge and dash lines? You can just draw it anywhere you want. There's no fixed way. Okay, maybe you all think about question 13 while I address Jing Shen. Okay. Jing Shen, so technically what happened is where's my Apple Pencil button? Oh, there you are. Okay, wait, sorry. Dixon, if you look at this molecule, right? The 4 groups, you can put them anywhere you want. But so actually you don't need to, there's no dictation of where should go where. So as long as you fill up the 2 solid line with the bow line and the dash line, with these 4 groups is good enough. But what you need to take note of is, so what you need to take note of is, they must attach to the correct atom. So usually, for example, here it must be connected to the C lah, and then things like OH must be connected to the O. Cannot be connected to the H law. Okay, next, Trisha. I mentioned 6. Did I mention 6? No, I didn't mention 6. Okay, I'm going to show you what I mean. Yo. Okay, no, 6 configuration. No, configurational are not enantiomerism. So configurational is a third type of stereoisomerism. Oh, why you keep rotating? Okay, so why I keep rotating is because when you have a normal bond like this, so any normal bonds will be able to rotate. This is a free rotation, correct? So if you recall just now cis trans, we were saying that if you are in a CC double bond, there's no free rotation. Okay, so if it's a CC double bond, there's no free rotation. Give me a minute. Okay, so if it's a CC double bond, there's no free rotation. But if it's a CC single bond and any single bonds, there will always be free rotation. So because there's free rotation, right? What happened is a molecule that supposedly have a mirror image can still have optical activity when the molecule rotates into this manner. So if you see in this manner, it no longer have that mirror image. So then it will have it will no longer have an internal plane of symmetry. So then it will start to have its mirror image. Configurational isomerism, yes, they are stereoisomerism, but usually we find them in H3 syllabus. So this one is not in syllabus. But why did I mention it is because even though it's not in syllabus, you need to still understand that the CC bond can be rotated. So that for certain molecules that if you see in question 13, the mock paper, you will need to rotate the bond in order to understand the molecule. So that is why I'm talking about it. Trisha, did I clarify properly with you? Okay, so what happened is you must take note. The molecule that I'm showing you now have 2 chiral carbons, correct? The 2 chiral carbons will give you 4 sets of four enantiomers, 2 of each set. Yes, no. So no, you cannot think of just stereoisomers because stereoisomers is everything. It includes cis-trans, enantiomer, and configurational. So basically what happened is you think of it more like this way. Okay? The one molecule got 2 chiral centers, correct? So one molecule got 2 chiral center. The 2 chiral center will give you 2 sets of 4 enantiomers plus 6 configurational isomerism. So what I'm trying to tell you is this molecule can have 2 types of stereoisomerism. One is enantiomerism, one is configurational isomerism. You're clear about this? As that meaning that this molecule can have 2 types of stereoisomerism. One is enantiomerism, whereby 2 carbon, 2 square, so 4 enantiomers. It can also have 6 configurational isomer, which is a second type of isomerism. But usually why we talk about configurational isomerism is because we need you to understand that the bond can rotate. So what you need to take away from configurational isomerism is that the bond can rotate. Yes, correct. So in total, there's 24 stereoisomerism. Because 4 enantiomerism times 6, what? But during exam, please don't talk about configurational isomerism. I'm telling you now is because I need you to understand that the bond can rotate. So once the bond is able to rotate, you'll be able to understand question 13. Trisha, good not? Or not good? Not good, then you wait for me, end of the class, you come and find me again. Okay, so let's take a look at MCQ question 13. Okay, what is the main problem here? Okay. So let's take a look at question. Okay, so this is it. Okay, what is the answer? Okay, come, let's do a show of hand thing. Okay, who choose A? Okay, I have 4 people choosing A. 5. Okay, who choose B? I have also 5. Who choose C? Okay, 3. Who choose D? Okay, no one. What is the correct answer? Answer is A. So answer is A, and I'm going to show you why. I think the main problem some of you think of is okay, so A is the answer, and I'm going to review why now. Okay, first thing is 1 is confirmed the answer. Why? Because if you think about it, this carbon have 1, 2, 3, as well as 4. Correct? So there's 4 different groups. Confirm this one got enantiomerism. There's no internal plane of symmetry. There's 4 different groups attached to it. So immediately B and D is out already. So your answer is just A and C. Okay? Okay, next. Between A and C, so 1 and 2 confirm is the answer. So which means that 2 is the answer, but some of you may not be able to see 2. Okay, so what is happening? Okay, so I need to show you again. Okay, so we focus on these 2 carbon here. One is a bowl, one is, so you have 2 bowls of hydrogen. Who is Mr. L? Don't you? Okay. So if you see here, your two hydrogens in the front, your two bromine at the back. Correct? Then what happens is you have a CH. This two is your C2H5. Correct? But if you look at the molecule, one is pointing up, one is pointing down. Right? Oh. Oh, okay. So one is pointing up, one is pointing down. Why? Never mind, don't worry. Okay. This is why. Okay, so look at my molecule. Focus on my molecule. Okay, I need to see myself. So if you look at the molecule itself, this is the green color group. Green color and the green color group. One is pointing up, one is pointing down. Correct? Then what happened is this carbon that is on the left-hand side, the hydrogen is pointing out, the bromine is pointing at the back. Correct? So which means that if you look at the other side, carbon number 2, hydrogen pointing out, bromine pointing at the back. So this is the molecule. If you rotate it this way, they are not mirror image. There's no internal plane of symmetry. Correct? So 2 is the answer. So how to do this during exam? You have to try and rotate this molecule, the C2 molecule. So this is the reason why I'm teaching you configuration isomerism, because this bond that I'm going to put in dark blue right now needs to be rotated in order for you to examine the molecule. I said, so during exam, you know what happened? You don't have molecular modeling kit. What you do is you think of pen. You use pen and you use whatever you can get. So you use all your pens as your help line. So you think about it this way. My apple, this is the green color bond. This is the CH2CH5, the ethyl group. This is the hydrogen. This is the Br. So you have to rotate the molecule such that the green color goes downwards. Then you'll be able to see that your Br will end up going forward. So meaning that you have to redraw your molecule in this manner. So what you do is you try to redraw the molecule. People online, give me a minute, okay? So if you see, technically you redraw it this way, then you rotate the molecule. This one, I cannot help you if you don't have an imagination. Must be able to imagine. So you must slowly train yourself up in your imagination. What I want is this green color, this part here, to now go down. So I have to rotate the molecule such that it goes down. So which means that the Br that was at the back, at the bottom here, when you rotate, it will go to the front on the top. Can see, right? So if, for those of you who cannot see, think of it this way. This is the Br, this is the hydrogen. You need to rotate, then no. So for those of you who cannot see, look at my screen now. Okay, this is the ethyl group. This is the hydrogen. This is the Br. So you need to rotate the molecule this way. Correct? So imagine this is the Br, right? You rotate. Now the Br is in the front. So when you rotate, then it becomes like this. So 2, no mirror image. Okay lah, cannot. Can see. Now, if you cannot see, I basically is look at this molecule. So later you can come in front and look at this. Okay, come, let me address people online. So technically it is still considered as the same molecule. It's just that it is a different configuration. Same, it's still the same molecule, it's just that 3-dimensionally it's looking different now. So that is to answer Trisha's idea. If you rotate and it's not symmetrical at all points, if you rotate, it's not symmetrical, it rotates plane polarized like. Yes, correct. So if you rotate and then you realize there's no line, internal plane of symmetry, then it will be able to rotate plane polarized light. Trisha, maybe why I want to explain to you why you need to rotate the molecule is because you need to figure out whether there's an internal plane of symmetry. If you look at 2 itself, there's no internal plane of symmetry, correct? But if you rotate the molecule, then there will be an internal plane of symmetry. So as of now, 2, you cannot see whether there's an internal plane of symmetry, which is the reason why you need to rotate the molecule to determine if there's an internal plane of symmetry. Because for 3 and 4, if you rotate the molecule, there will be an internal plane of symmetry. So what do I mean? So, yeah.
The configuration one won't affect polarized light.
No.
Now, okay.
Oh. You mean Trisha's question was whether it will affect plane polarized light, is it?
Yeah.
Yes, I think okay, maybe Trisha, that's a good point. Trisha, what I need you to understand is this. The only one that can rotate plane polarized light is enantiomerism. Okay, so let me go back to the notes again. So technically, when we talk about stereoisomerism, there are altogether 3 types: cis-trans, enantiomerism, and configurational isomerism. The only one that can affect plane polarized light is enantiomerism. Configurational cannot affect light. Cis-trans also cannot affect light. So you can keep rotating the molecule, but if you have a new configuration, it will not affect light. Why one question, everyone like? This one is A-level question, I'm not lying. 2022. Okay, go and check. If I'm not wrong, if I remember correctly, EJC last year prelim already tested. Yeah. So you all need to understand how to deduce the molecule. So for some of you, okay, let me just explain the last 2 molecules. So in the last 2 molecules, what happened was, if you look at the molecule itself, the BR is in the front. Okay, you all see how I rotate the molecule, okay?
That's nice.
What?
Okay. So what happened is, if you look at your option 3, option 3 is the green group is the ethyl group. One is on the top, one is at the bottom, correct? Then what happened is, the white color atoms is your hydrogen, the yellow color atoms is your bromine. So what happened is, on the carbon on the left, the bromine is at the back. On the carbon on the right, the bromine is in the front. So when you rotate the molecule such that the green color is now at the bottom, this has a internal plane of symmetry. Correct? So which means that it cannot rotate the light. I said, same thing for 4. 4, if you try to rotate the molecule, you realize that the BR that was supposedly in the front, same thing, so green color is the ethyl group. Now your BR is in the front, the other BR is at the back. So when you rotate the molecule such that the green bonds is now facing bottom, the 2 BR atom on the front will cause this thing to have an internal plane of symmetry. So that is why 4 also cannot rotate plane polarized light. So if we look at the option, that is why 3, 4 cannot. Because if you try to rotate the molecule, so you focus on the blue bond here, try and rotate the molecule. So if you try to rotate the molecule, upper, never mind, it's okay, I'll clean it. Don't worry, don't worry. So what happened is, the 2 BR will now be on the back and the 2H will be in the front. For D, also the same issue lah. No stress, don't stress. It's fine, no worries.
So actually,
Yeah.
so long as one configuration that doesn't have that has a line of symmetry, that means it not rotates.
Plain polarized light, yeah.
As long as one.
As long as that configuration have an internal plane of symmetry, it cannot rotate plane polarized light.
What we did there was you
Yeah.
rotated it.
Yes, correct.
So that's not what they gave you, but you rotated out your own initiative.
No, but you have to rotate. Yeah.
Taking into consideration all the rotation.
Because once again, you have to really consider the question itself. Because technically this one, they are just asking the molecule as a whole, correct? But certain molecules in certain configuration can rotate light, certain configuration in certain molecules cannot rotate light. So technically what happened is, if they ask you to consider the molecule, you have to consider all the configuration and see which one has an internal plane of symmetry.
Okay.
If let's say they are really talking about one molecule, but sometimes it can rotate light, sometimes it cannot, then basically they're asking you for configurational isomerism. So like, for example, this question here, just now, the one on the top. So for example, like this is the same molecule, correct? This is just one molecule. But they say that this molecule sometimes can rotate light, sometimes cannot rotate light. So you are talking about the same molecule, different configuration, then you have to consider the configuration itself. Correct? But now what happened is that if you go back to question 13, what they are telling you is, I want to see whether that molecule itself can rotate light. So whether that molecule can rotate light or not, you have to consider all the configuration. And see which configuration have an internal plane of symmetry, then cannot. Because for molecule 2, no matter how you rotate the molecule, right, it can never have a internal plane of symmetry. It's just that 3 and 4, there is one. So that one causes the molecule not to be able to rotate light. Yes. You mean different configurational? The rotation one? Different configurational one can. But because they're asking you the molecule, they didn't ask you whether this configuration of the molecule. Oh. So because molecule-wise, you have to consider all.
So long as one form of the molecule is able to rotate, then it can.
No, as long as one form cannot rotate like the whole molecule can. Usually we don't see as one can do, all can do. It's more like if one cannot do, that configuration cannot do, but the rest maybe can. So I think what your question is saying is, because they draw you in this configuration, so what you need to think of is this configuration. Am I correct? So technically, that is the problem with this question, no? Because the problem with this question is that the official answers say that it's only 1 and 2 because they want you to consider all the configuration, not just the one that they give you.
How do you know?
So you have to look at whether they ask you which molecule. If they just mention the word molecule, that means you have to consider all the configuration of that molecule. So you have to consider the configuration of all 4 molecules and see whether is there any internal plane of symmetry. You have to consider the whole molecule. If they want you to consider certain configuration, they will say that I'm giving you this molecule. Okay, certain configuration can give you this, can rotate plane polarized, like certain configuration cannot. They'll be more specific in that sense if they want you to consider the configuration. Okay. Hey, wait, where am I? Okay. Okay, I can explain to you 3 and 4. Wait, Jing-Shen, if you don't mind, you stay back for 5 minutes later. I will explain again. Can? Okay, next we are gonna look at alkanes. So let's just straight away look at the mock paper itself. Okay. In your understanding of homologous series, the most important part you need to understand. Okay, let me go back to my notes. Sorry. I'm going to go through mock paper 5, but give me a minute. Okay, so first thing first, if there's anything I need you to take away from today is that for each homologous series, you must understand your molecule very well. So meaning that you must understand the functional group super well. Okay, as you study organic chem, your focus should be on the details involving the functional group. Okay, so for example, in alkanes, the functional group, there's no functional group. So the molecule as a whole, generally is quite unreactive. Why? Because number one, the bonds are very strong. Okay, so usually, if you go and look at CC bond, CH bond is about 300 to 400. So the bonds are super strong. Next, they are also not very polar. In fact, they are not polar at all. Correct? So as a result, if they are not polar, what could potentially happen is that they cannot be attacked by electrophiles or nucleophiles. So before I go on, I need to explain to you the 3 reagents you're going to get in your organic chem. So in organic chem in general, there will be 3 reagents you will tackle, which is electrophiles, nucleophiles, and radicals. Okay, dissect the word. Yes, at the very end. So electrophiles basically is electron seeking. So I always like to draw my electrophile as an E+. Why? Because usually your electrophiles are positively charged. That's why they go and seek negative charges. I said, so you think of electrophiles as E+. Positive charge, go and find negative charges. Nucleophiles are Nu minus. So they are negatively charged. They will go and find positive charges. Lastly, for radicals, okay, for radicals, take note, radicals usually they are something with they are substances with unpaired electrons. Wait, Trisha, you want to say something, is it? If you don't mind, can you just type it out? Thanks. So what happened is, remember, electrophiles have positive charges, nucleophiles negative charges. Radicals is just single unpaired electrons. So what happened is this. With alkanes, the issue is that because they are non-polar, right? They don't have positive charge or negative charge for electrophiles and nucleophiles to attack them. I said, so they are non-polar, which means that they are neither electron rich nor electron poor. So they are not targeted by nucleophiles and electrophiles. So as a result, they have to do free radicals because free radicals is meant for them. So here I have summarized the chemical properties you need to know. What I want to talk more about is the reaction mechanism. So what happened is you need to take note in reaction mechanism for free radical substitution, there's always 3 stages. Stage 1, initiation, stage 2, propagation, and stage 3, termination. Okay, what is the key essential idea for each stage? That is what I want to talk about before I go on and look at the mock paper. So you must remember, initiation, basically what you want to do is you want to produce the radical. So stage 1 is initiation stage is to always form radicals. Understand? So it's to form radicals. Next, stage 2, what is going to happen is this. Your radicals that you form in stage 1 will go and attack one of your reactant. Usually it's the alkane to form an alkyl radical. Okay, so basically the idea is this. Radical that you form in stage 1, initiation, will react with your alkane to give you a new radical. Let's call this radical 2. So which means that radical 1 will attack alkane to form radical 2. Then what happens is radical 2 will then react with the chlorine, the halogen, your second reactant, to form back radical 1. So basically the cycle goes like this. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So propagation is just keep doing step 1, step 2, step 1, step 2, step 1, step 2 until everything reacts finish. I said, so the cycle will just keep going on. It will be from stage 1, go to stage 2, stage 2, form back stage 1. Then you go A, B, like that. What you need to understand is how to write out the 2 equations. So you must remember, radical comes from initiation, react with one reactant, form radical 2. Radical 2 then react with the second reactant to form back radical 1. This is also what you will see in the depletion of ozone layer. So basically your chlorine reacts with O3 to form a O radical. The O radical then reacts with chlorine gas to form back the chlorine radical. I said, So take note in your school notes, your teacher should have talked to you about the depletion of ozone layer. Please go and read about it. Understand? Then basically in termination is like all the radicals just react with each other. So the final stage termination, basically your radicals will react with each other to form side products. So termination is not propagation terminated, is propagation will keep continuing on until they feel like, okay, it's enough already. Then they will start to do termination. Okay, now the amount of reaction you need to write is this. Initiation, stage 1, 1 equation. Propagation, stage 2, 2 equation. Termination, stage 3, I expect 3 equation. If your teacher tell you 2, no, it's 3. Okay, your teacher should not be telling you there's 2 termination steps. It should be 3 termination steps. Okay, with that in mind, what happened is this. I need to go through this before I do anything else. This part here. Okay, if you look at this molecule, okay, this is propane, right? So technically, if propane was to do free radical sub, the hydrogen can be replaced with a chlorine, correct? So if you replace it with a chlorine, if you think about it, the square hydrogen can give you 1 isomer. The circle hydrogen can give you a second isomer. According to maths probability, it will be what? 6:2. This is the theoretical probability based on the hydrogen atoms. But what is the actual probability? It's flip, meaning it's about 2:6. So why is it that the primary radical or the 1-chloropropane is the minor product, even though it's expected to be the major product given that there's 6 possible hydrogens for it to form 1-chloropropane? And why 2-chloropropane, supposedly the minor product because there's only 2 hydrogen, can end up becoming the major product? And that is because of the stability of the radical. So if you think about it, if I take out the green hydrogen, one of the green hydrogen, I form a primary radical. So primary radical, why is it called primary? Is because if you look at this C with the dot, there is 1 alkyl group. But if let's say the second one, that means you take out the pink hydrogen, you form the secondary radical. It is a secondary radical because there's 2 hydrogen group, 2 alkyl group. So 1 alkyl versus 2 alkyl. Why is the 2 alkyl more stable, leading you to the major product? It's because you need to remember this. Alkyl groups are what kind of groups? Electron donating. So your alkyl groups are electron donating. So you have more electron donating alkyl group. It gives more electron to the C with a dot to increase its electron density. Now you must remember this. Radicals are not like carbocations. Radicals is the more electron you give me, the more stable I become. So usually we call radicals the mad dogs of organic chem because they will anyhow attack anyone they see. As long as you have an electron, I will go and attack you to take your electron away. So the more electron they have, the better. Which means that when you have 2 groups that can give electron to this C with a radical, it's going to increase a lot of its electron density, making it more stable. So that is the reason why it leads you to the major product. Whereas if you see the first one only got 1 R group to give that C with a dot. 1 R versus 2 R. 2 R is better. I said. So in terms of radical is the more electron density, the better. But if later when you learn alkenes, you're dealing with carbocation. Carbocation is this. If you have a plus charge, never mind, I'll go through carbocation in about 5 minutes time. Okay, never mind, I'll just go through carbocation now. Okay, so that is what I want to say about alkenes. Okay. Now for alkenes, what happened is, let's talk about the functional group. Okay, alkene functional group, how do you understand? You must understand the CC double bond, okay? So you have CC double bond. If you focus on the double bond, there's how many electron there? 4 electron, correct? So it's very electron rich. So there's high electron density. Yes, correct. Radical 2 is an intermediate. So for CC double bond, take note, for alkenes, you have a CC double bond. The CC double bond makes it it has high electron density because of that pi bond. So it makes it very electron rich. So when you have electron rich, who will you gonna attack by? People who are looking for electrons. Who are people who are looking for electrons? Electrophiles. So that is the reason why they get attacked by electrophiles. Yes. I heard your question. Yes. The word phile means looking or liking. So if it's electrophiles, I'm looking for electrons. So if you are electron rich, you will attract electrophiles. If you are if you are electron poor, you will attract nucleophiles. So this is also the reason why the mechanism is called electrophilic, because the initial attack is by an electrophile. So let's talk about the mechanism itself. So what you need to remember is there are 2 steps to the mechanism. The first step is whereby you get attacked by an electrophile. So primarily, I need to highlight to you, where are your electrophiles? HBr is the electrophile for this reaction. You need to remember this is H-Br, whereby Br is more electronegative. So delta minus, delta plus. Must remember, electrophile is positively charged. So this is your electrophile. Next, for Br2, basically what happened is you have a Br-Br bond. By right, it's not polar, correct? But you know that electrons are not static. They will keep move around. So there's an instant of time whereby they move more to the right-hand side. Delta minus, delta plus. And that is where the electrophile is to go and attack the CC double bond. Finally, for water, it's like this. Delta minus, delta plus. The hydrogen is the positive, is the electrophile. So what happens is, when you do the initial electrophilic attack, you must know who are your electrophiles. So I've highlighted to you what are the electrophiles in the 4 reactions you're expected to know. Okay, what do I need from you in the mechanism? I don't need you to describe to me. So I wrote it here is because I need you to understand the step. But this is not required, meaning that you don't have to write for me step 1 electrophilic attack. I don't need that. I just need you to be able to draw. So which means that I'm looking for this drawing here. Okay, so in this drawing, what do I need? Number 1, I need you to, from the CC double bond, go and attack the electrophile, which is the one with the positive charge. Now, your molecule will undergo polarization. So I need you to show me the polarization, and I need you to show me delta plus, delta minus. Now, most importantly, if you never label this step as the slow step, the whole step is wrong. So slow step is the third key feature. So key feature number 1, key feature number 2, key feature number 3. Next, when you want to decide how to put your electrophile to your CC double bond, you have to apply Markovnikov rule if it's unsymmetrical. So for some of you who are unfamiliar with when to apply Markovnikov rule, it's applied in step 1 of your reaction mechanism. When you have an unsymmetrical alkene. So if your alkene is symmetrical about the CC double bond, then there is no point in you thinking of Markovnikov. I said. Now, why do you need Markovnikov? Because like just now, the discussion here, we are always trying to predict who is the major product. Correct? So every time you consider one reaction, you have to think of who is the major product. And you must draw the major product. Because if you draw the minor product, your teacher can mark you down. Not give you 0 lah, but maybe will deduct 1 mark. So when they always talk about a reaction, unless they specify, if they never say anything, you should always give them the major product. So this is the reason why you apply Markovnikov, because for an unsymmetrical alkene, there are 2 positions in which you can put the electrophile. So if you look at the diagram here, I have this is my CC double bond, correct? I can put the electrophile, which is the Br, on the circle carbon or the square carbon. It will lead you to, once again, 2 different results. So for the one with the square carbon, I don't use purple, I use blue. So for the one with the square carbon, take note, you put the Br there, the other one must have a plus charge. Why must have a plus charge? Because you are adding a delta plus. So the plus charge must be there. Because the Br carries the plus charge. But when the Br forms a bond, technically he gives the plus charge to the carbon that was left behind. So this is the carbon with the plus charge. Now, if you look at this carbon with a plus charge, how many alkyl groups is attached to it? This whole thing is considered as 1. Okay. Now, if you put it to the circle atom, that means the Br added to the circle atom, you will end up with this carbocation intermediate, whereby your plus charge is in the middle carbon, and then you have 2 R groups. So if you see, technically, what is the difference here? How do you apply Markovnikov rule? Very simple, just think of it this way. You put your electrophile to the carbon of the CC bond with the most number of hydrogen atoms bonded directly to it. Take note, it's bonded directly to it. So if it's part of an alkyl group, it's not considered as a direct bond. So I want you to look, the pink color carbon, this circle carbon, have 2 hydrogen attached to it. This square carbon have 1 hydrogen attached to it. So based on Markovnikov rule, what we will try to do is add to the pink carbon so that we form the more stable carbocation. So why is this carbocation at the bottom more stable? Same argument like just now. 2 alkyl group, 2 times the electron donation. So you donate electron to the positive charge, what will happen to the positive charge? So you have a positive charge, you give it some negative charge, the positive charge will drop down. When the intensity of the charge decreases, the molecule will become more stable. So this is a very contrasting idea to your radical. Radical, what happens is you want it to have more electrons, correct? Now here what you want is, you don't want the charge to be too high. You want to lower the charge. Okay, so must remember, here you want more electron density. Radicals, more electron density. Because more electron density will make the radical more stable. Here, what you want is you want the charge to be lesser. So how to decrease the charge? If you have more alkyl groups, more electron donating alkyl groups, you will have a stronger electron donating effect that will help you to disperse the charge or decrease the charge. So that's why if you see here, 2 alkyl group better. So in other words is, at the end of the day, for both scenario, you want more alkyl group attached to the carbon you are concerned with. Because with more alkyl group, they either raise the electron density or they make the charge, the positive charge, less intense. So it just depends on what scenario you have. Now, so what happened is, this is the reason why, if you think about it, for this molecule here, I have 1 hydrogen. Here got 2 hydrogen. So I'll put it to this carbon here. So when I put it to the red carbon becomes like this. Then this carbon with still 1 hydrogen, you put a positive charge. Now comes the interesting part, which is step 2. So if you recall what you learned in organic chemistry in O levels, when you do aqueous Br2, your O answer was the CC double bond, put 1 Br, put 1 Br. Correct? But if you look at A levels, when you use aqueous Br2, it's no longer there. 1 Br, 1 OH. Why? Because your carbocation ion is positively charged, which means that as long as I have a negative charge or I have a lone pair, I will want to attack it. If you put it in aqueous Br2, you have a huge amount of water. Water, the oxygen have a lone pair, so the lone pair will go and attack the carbocation ion. So you must take note, in your step 2, that means someone will cut your Q. So by right, this Br minus that you see here is supposed to go and attack the carbocation ion and complete the reaction. But this Br minus gonna cut Q. By who? By water. So you must take note, in step 2, there is a possibility that your carbocation ion may be attacked by other nucleophiles, which are usually your solvents. Now, so I use the most simple example, which is aqueous Br2. So in aqueous Br2, what happened is the water will go and attack the carbocation ion. Now, you must know how to draw this, because nowadays, all the schools want people to draw this. So how to draw this is your O, so your water looks like this. When the water go and attack the molecule, it forms a bond. So now you have 3 bonds, correct? When oxygen have 3 bonds, it means that it needs to have a positive charge. But oxygen is electronegative. So it cannot have a positive charge. It does not like positive charge. So what it will try to do is push a H plus out. So it will take the electron from this H, give the plus charge to the hydrogen, and push it out. So if you have, so take note, this intercept attack, right? Who can attack it? Usually nucleophiles. Nucleophiles have what? If you see any lone pairs or you see any negative charge species, usually they are the ones that have a higher chance of attacking your carbocation ion than the supposed nucleophile, which is formed after the first step. Now take note, so which schools have come out what weird shit? Nanyang got 1 year, they told the student that the Br2 was dissolved in NaNO2 solvent. So NaNO2, what happened? You have Na plus, NO2 minus. So what happened? The NO2 minus, because it's the solvent present in large quantity, attack the carbocation. So so how they draw is, and they ask the students to actually draw. So when the student need to draw, they need to draw something like this. Lone pair, attack, fast, and so that was the answer for that year. You get ready lah. So as long as you see Br2, that means this thing, right? The X2 not in polar, not in non-polar solvent, meaning not in CCl4, in some weird S solvent. Then you just get ready. Step 2, confirm is got someone cut your Q1. Now take note, so what happened is, I don't know which school, they told the student don't need to learn it as what? Heat with reflux. But take note, you need to know heat with reflux. But you do not need to know the exact temperature. Last time, my time need to remember the temperature. So for example, like this case, I don't need you to remember 200 anymore, but you need to remember that there must be heat. So exact temperatures, exact pressure, don't need to know. Just need to know it as with heat, without heat, things like this. And heat in what form? Because if you learn alkyl halides, there are a few forms. So it's heat in a sealed tube, heat with reflux, warm or normal heating. That kind of description you still need to know. Okay, I'm sorry, but if you all don't mind, just give me about 7 minutes. I just want to explain question 16. Question 18 actually quite easy, but question 16 is not. So I just want to explain question 16. Okay, just give me 7 minutes. Yeah. Yeah, I will. Give me a minute. At the very end of these 7 minutes, I'll share with you the answer, okay? Question 16 is not your... So question 16, right? Technically, what some of you are thinking is free radical sub. But the answer is not free radical sub. It's free radical addition. Okay, now let me tell you what you will encounter in A-level chemistry with regards to organic chem. Organic chem is one of the branch of chemistry that has a lot of application. So they can teach you all the free radical, electrophilic things like this, but they will never really test you on the actual thing that they teach. Rather, you need to learn how to apply. So what happened is, I need you to understand the free radical substitution mechanism and then apply it to question 16. Because question 16 ultimately is not purely free radical sub. It's free radical addition. So you can find the answer to A and B later, even C. What I want to focus more is D. So step 4 occurs in 4 separate reactions, A to D. Okay, now we will look at part 2. So if you recall back what I taught you about free radical substitution. So in free radical substitution, there are 3 stages. Stage 1 is you form the radicals through homolytic fission, correct? Then the radicals will react with a reactant, then the reactant will react with another, then the radical will react with one reactant to form one radical, and then that radical will then react with a second reactant to form back your initial radical. Then finally is termination. So you need to be able to recognize the 3 stage and look at the question and identify which of the 3 stage it is. So if you look at this question, stage 1, homolytic cleavage of the ROOR. Basically what happened was you have ROOR, half arrow, RO radical. So what does this remind you of? Which stage? Initiation. So stage reaction A, initiation. That is what they mean by the name. The name is to name which stage of the reaction. Next, stage 2, what happened? So by right, some of you will think CC double bond, electrophilic addition. But you look at the previous part, it's radical, where got electrophile. So this is not an electrophilic addition reaction. This is in fact a free radical addition. So how do you do the free radical addition? Technically, what happened is this. You see your CC bond, right? Okay. So what happened is, if you look at the middle bond here, there is 2 electrons. If you do free radical, that means you give 1 electron to this carbon and 1 electron to this carbon. Then what will end up is the green bond will break and they each have a radical. Then what could potentially happen? So the RO radical will then form a bond with the carbon. I said, okay, I draw this in stages. So what happened is this. CC bond, 2 electron, 1 go to this carbon, 1 go to this carbon. So you form something like this. Then your RO radical will then form a bond. And you will get this. So if you think about it, what happened is you have a radical 1, attacking reactant 1 to form radical 2. Then what will radical 2 do next? So radical 2 will then react with another CC bond whereby if you see there is, look at this red color bond, there is 2 dots, 2 electrons. So 1 electron used to form a bond with this radical, the other electron go to this carbon. So you end up forming this. And then the reaction will just keep continuing until you get a long chain of CF2. Some of you may be thinking, is this really a prelim question? Answer is no, this is an A-level question in 2022 or 2023. So don't think that your A-level questions are very easy, they are not. In fact, I pick all these questions because I think I need you all to understand that A-level questions are not as easy as you think it is. Because some people have the impression that prelim question very difficult, but A-level can be equally difficult as well. So basically what happened is that, if you see, I've described to you, so this is reaction B, right? The RO go and react with a CF2 molecule to produce a new radical. So this is your propagation. Then the propagation continue on, whereby the radical go and react with another CF2 to lengthen the length until you end up with a lot of this. So this is also propagation. But what happened is, then your final stage is two of these radical combined together. So I don't think I need to draw lah. So technically, yeah, I don't need to draw lah. Okay, I'm not drawing. Okay, so D is termination. Now, they ask you to suggest a name for this mechanism. So technically, you are dealing with radicals, so there should be the word free radical. But if it's a substitution, what you're doing is you take out one, you put in one. Am I correct? This is not a substitution because you are adding things across the CC double bond. So this is a free radical addition. This one not in syllabus, but can they test? This is an A-level question, so clearly they can test it as an application, and you need to know how to apply what you learn in free radical and electrophilic addition. Then next, in step 4, they ask you to draw the mechanism for reaction A and reaction B. So technically, reaction A, I already draw it out, is this. Reaction B, technically, we will synthesize this. So I don't need you to draw until so scary looking. It will look something like this. I am also doing this is because 2022, you know, like some of your teachers like to use A-level questions. So this could potentially be an A-level question that they adopt for your promo papers. So focus on the pi bond. The pi bond got 2 electrons. So what happened is 1 electron will be used to form a bond with your RO minus. The other electron give it to the other carbon. So you end up with something like this. Now what you should try to do is mask away the dot, because by right the dot not supposed to be there. But I'm just putting the dot there to show you what happened to that 2 electron. Then the rest should be quite okay. Yeah, the rest should be quite okay. Okay. Okay, I know some of you are looking for answers. Give me a minute. Okay, so there are a few things I need to clarify. Okay, wait. One by one. Okay, so now for just bear with me for 5 minutes. I will wrap up everything. I think, yeah, just let me wrap up everything. I'm gonna end in 5 minutes time. This is the last question I'm gonna go through. Okay, so there's a few things that I need to share with you, given that today's class focused a lot on organic chem. I need to tell you what your J2 seniors always face in terms of problems, and then what you should do to not repeat their problems. So technically, if you realize your organic chemistry is 10 chapters, it will take you about 6 to 8 months, meaning that the next time you stop organic chem will be next year in your J2 year, probably around April or May. Now, what happened is 10 chapters, but what is the number of reaction you need to learn in each chapter? If there's a mechanism, usually it's less than 10. If there's no mechanism, for example, like the chapter on alcohol, it can go up to 20 reactions. So in total, the whole syllabus itself, you need to remember 100 to 120 organic reactions just for A levels. So please don't repeat your JC2, your J2 senior mistake. What they always like to do is, for WA1, they think that they can remember everything. And I still haven't teach finish yet, but they think they can remember everything. So they start memorizing the night before. Then they realize they cannot finish. Then what happened is, after they learn their lesson, then they say, okay, let's start 1 week before. So in their WA2 during the June holidays, they play first 2 weeks, then last 2 weeks start to memorize. Then they realize also not possible. Why? Because I do not need you to just remember. You need to learn how to apply. So pure memorization will not work. You need to internalize the organic chem reaction in order to apply it. So I have one student from past year who did this. And this is my advice to everyone. You are starting out with alkanes and alkenes. For your promo, it's not that difficult. But actually, every chapter you are done, go and start compiling everything you need to know about the organic reactions. So for example, like alkane, you need to compile nicely one. Alkene, you need to compile nicely one. If you are not a table person, you are a mind map person, then go and do the mind map. Because I have one student took the brothers' 3 drawing block, paste together, and then start to link up everything. Understand? In order to help you, the revision kit has the summary of all the reactions. But to be honest with everyone, in order for you to really understand the reaction, you cannot be spoon-fed here. So you need to compile it on your own one time so that you commit to memory. Then as you revise second and third time, it will become easier. If you rely on me giving you this, maybe promos you can pass, but I don't think WA1, WA2 next year you're going to pass very well. Okay? So that is my advice to everyone in terms of organic chem. Finally, I need to share with everyone some piece of information. Can I send you this? Send you what? Cannot. Wait, Javen, later you talk to me. Okay, next. Okay. So technically, at Overmark, we have a few resources given the curated notes. Maybe you saw a glimpse of it just now. There's a lot of mock exam revision. We are holding J2 hands-on prac next year. So I think next year, the JC will have hands-on prac at Overmark. That is something that is quite rare outside. So you may want to consider. But more importantly, to help you with your promos, technically, there's now the EOY booster class. So if you can see today, I only went through organic chem and it's already taking up 3 hours of our time. But there are other chapters that I think you are also quite weak in, probably kinetics, probably energetics, probably equilibrium. Some of you, chemical bonding. So if you are interested in this only a 4-week intensive EOY class. So it will be held between 9 Sep to 16 Oct. That is roughly where your promos will end. It's $100 per lesson. Okay, you don't need to sign up all 4. You can sign up to the day that your promo ends, and then after that, that's it. But what will I do in these 4 classes? I think that is probably what I want to stress more on. So I will not be teaching a lot of content. We will be spamming a lot of the mock papers or past year promo papers, specifically from last year. Okay, so I'll be selecting 4 promos papers to go through, and then that is where I'll start to consolidate all the different chapters together. And you should realize this, all your questions are not standalone questions. So one question can have organic chem with kinetics, and then with energetics, and then with equilibrium, like what you see in the mock paper. Okay. So if you're interested, you don't have to sign up by 8 Sep. You just contact the admin people, they will help you. I think more of importantly, because I cannot finish the paper, I would need you to scan this QR code for the answers. So for those online, if you are looking for the answers to the whole mock paper, this is where you can find them. Okay. Primarily, take note, I will also be going through topics like acid-base as well as arenes in the booster class. Okay. Last but not least, if you don't mind, please, if you can, leave a feedback. You can scan and then leave a feedback, and then after that, show either me or the people outside, and they will pass you a free foolscap paper from Overmark. Okay. Yeah, I guess that is all. Anyone who have any questions, can stay back and ask. If not, then I hope y'all understand organic chem better. If you have any more questions that you need to clarify, please do stay back and ask. Okay, then if not, you're good to go. Okay, go. Okay, for the revision kit, take note, revision kit is meant for physical students, but what you can do is ask the admin, they might be able to arrange for you to come down and collect the revision kit, because we don't have soft copy of the revision kit, only the hard copy. So revision kit, that means the whole kit itself for those who are online. If you want a copy, you have to arrange to come down to one of the centers to collect lah. Okay? Bye. Elise, your question, you okay now? The one about the configuration, that part. So just need to remember this. Most exam questions will not ask you for configuration. So when they give you the molecule, you must see if there is one configuration that cannot work. If there's one configuration that cannot work, then technically that whole molecule by right should not be able to rotate light. I said it's only in specific questions then they will ask about whether the different configuration of that molecule. So for example, if you recall just now there was the if you recall, right, they draw this molecule for the student. Then they told them that this molecule in certain configurations can rotate light, in certain configurations cannot. So that is where they want you to consider the configuration. The real actual configuration. So that's where different configurations may be able to rotate light or not. But in general, A-level sense is as long as one cannot rotate, one configuration got internal plane, the whole molecule cannot. Okay. Can. Okay. I have a few questions I need to answer those that's online. Okay, Jing Shen, don't mind stay back. I'll clear with you. Let me just see. Okay, I need to speak to Trisha and Jing Shen and yeah, sure. Yeah, I know. It can help me. If they give the feedback form, can help me.
They give the form.
No, if they show you the feedback form, just help me pass the. Okay, I talk to Jing Shen first. Okay, come, Jing Shen. What is your issue? Thanks. Okay, question by question. Let's start with Jing Shen first. You mean the bye? Bye-bye. They just need to show you that they have completed the feedback form, and then after they just pass them one full scat paper. Okay, okay, Jing Shen, your question, I start off with the mechanism first, okay? Don't understand the mechanism. Okay, can. Which mechanism are you talking about? The application mechanism or the free radical or the electrophilic addition? I went through 3 mechanisms, so you need to be specific with me. Or is it all 3 cannot? All 3. I was in the toilet for the first part. Yeah. Okay. Okay. The session is recorded. But okay, never mind. I'll explain to you lah. Okay. Okay. we start off with the alkane reaction mechanism. So in the alkane reaction mechanism, correct? What happened is you are dealing with free radical sub. So in free radical sub, you need to know that there are 3 stages, and you need to know what the 3 stage entails. So in stage 1, which is called initiation, usually you're trying to form a radical first. So stage 1 is always trying to form the radical. Then in stage 2, which is propagation, what happened is, technically you think of it this way. The initiation, you produce a radical, let's call this radical 1. So radical 1 will go and attack one of your reactants, probably your alkane, most probably is your alkane, to form radical 2, which is an alkyl radical. Then radical 2 will then react with reactant 2 to form back radical 1. So this process will just keep repeating from A to B, and then A to B, A to B, until most of your molecules are gone. Then that is where they will start termination, stage 3. So in termination, that is where your radicals will start to form side products. Primarily, that is the main part of the radical. What could potentially come out as an exam question is the discussion here. So in the discussion here, what they are going to talk to you about is what is the supposed theoretical ratio and what is the actual ratio. Now, if you see, technically when you have a propane, correct, you can get 2 types of product. The one in green will form 1 chloropropane, and the one in pink will form 2 chloropropane. Supposedly, if you base it off probability of the number of hydrogen there is, 6 hydrogen, then there's a probability of it forming 6 compared to 2 hydrogen 2. So the ratio is about 6:2. That is theoretically what you would think of. But in reality, what you're going to realize is that the ratio is swapped. So the one that is 1 chloro, by right, we think that it might be the major product given that there's 6 hydrogens that can be substituted to form 1 chloro. But the issue is that there will only be about 2. So meaning that it's the minor product. And then for the second radical intermediate, or rather your 2 chloropropane will be the major product. That means the 2 pink color hydrogen, when you replace it, you will form a product that will give you the major product. So why is that so? It's because you have to think back of the intermediate it forms. So one primary radical, correct? You have 1 alkyl group. Secondary radical, you have 2 alkyl groups. So when you have more alkyl group, you have more electron density. Radicals are a very weird group of things. So the more electron density they have, actually they become more stable. So that is the first mechanism you need to know. Second mechanism you need to know is the alkene mechanism. So in alkene mechanism, you need to understand that you have a CC double bond. So when you have a CC double bond, that is an electron-rich substance. So which means that it will be attacked by what we like to call as electrophiles. So in your electrophilic addition mechanism, there are 2 steps. The first step is the electrophilic attack. The second step is the nucleophilic attack. Now, for the electrophilic attack, take note, you need to know what are your electrophiles. So I've written out the electrophiles and I've circled it in red. So those are the ones that will attack your CC double bond. So when you draw out the reaction, what I need you to take note of is you need 3 things. First thing is you need to have an arrow from the CC double bond point to the electrophile. Secondly is your original molecule need to have polarization. And then finally, I need to see the slow step. Then after that, what happens is then the attack will happen. Okay. Once again, when we talk about organic chem, we must always talk about who is the major product and who is the minor product form. So in this case here is where you will apply what we like to call as Markovnikov rule to unsymmetrical alkenes to predict the major product. So what is the rule all about? So the rule is basically you will take your electrophile and you add it to the carbon of the CC bond with the most number of H. Now, why do you want to do that? It goes back once again to inductive effect. So if you look at the diagram here, there's this is the two CC double bond carbon, the pink one and the blue one. So when you add your electrophile to the pink one, it will form the one at the bottom, while if you add it to the blue one, it will form the one on the top. Now, what you see is you will form what we like to call as a carbo-cation intermediate. Why is it a carbo-cation intermediate? Is because when you add the Br plus, the delta plus to the CC bond, you are introducing a plus charge. So what happens is the Br will be added to the carbon, then the other carbon will absorb the plus. So if you see, when I add to the blue carbon, the Br, the pink color carbon will have the plus charge. That is for the top part. And then for the bottom part is, if I add the Br to the pink color carbon, then the blue color carbon will have the plus charge. Now, what you want is to add it to the one with the most number of H bonded to it. So that when you have the plus charge, so if you see the one on the top, primary carbocation, the one at the bottom, secondary. So you have two alkyl groups, it can donate to this carbon and it can disperse the positive charge, making it more stable. So when it comes to radicals, it is more electron density, better. When it comes to alkenes, carbocation intermediate, you want your charge to decrease so that it becomes more stable. So basically, this is the two mechanisms that you must know for your syllabus. Then the third mechanism that I talked about just now was a application question that came from A levels. I think it was either 2022 or 2023. Probably it's 2022. So what happened was, in that question itself, they tested students on what we like to call as a free radical addition. So it's where you have free radical substitution plus electrophilic addition. Why? So technically, if you look at reaction A is you form radicals. So if you recall just now when we talk about free radical sub, the first stage is always trying to form the radical. So that is your initiation. Then if you look at B and C, technically what happened was, the CC bond, naturally homolytic cleavage, you introduce one radical to each carbon. Then the RO will then form a bond with one of the carbon, and that gives you your radical 2. Then your radical 2 will then continue to attack another alkene molecule to lengthen the chain. So that is where B and C, we see propagation. And then finally, the two radicals combine, and that's where you get termination. Now, if you want to describe this mechanism, it is not really a free radical sub because you didn't really take something out and put something in. But rather what you did was you take the double bond and you broke it and then you add things onto it, like what you see here. So that's why this becomes a free radical addition mechanism. But this one is not in syllabus. This one was acting as an application question. So this came out in, I think, A-level 2022 year, where they really want the student to apply what they have learned in free radical and electrophilic addition. Basically, that's all the three mechanisms lor. I like bullet train like that. 6 cannot. Yeah, okay, then can. Okay, wait, I think just now you have one more question, right? Okay, why 3 and 4 cannot rotate plane polarized light? That one you understand already, no? So why it cannot rotate plane polarized light? So just now there was some argument because they were saying that the molecule was drawn in this configuration. So if it was in this configuration, there's no internal plane of symmetry, it should be able to rotate plane polarized light. Now, this is the issue with A-level question. So if A-level question tell you that they want to deduce whether the molecule can rotate light or not, as long as one configuration cannot rotate light, That means one configuration got an internal plane of symmetry and cannot rotate light. Then the molecule cannot rotate light as a whole. So which is why if you look at this molecule, number 3, so number 3, if you look at my molecule, the green color one is the alkyl group here. So if you look at my molecule, green color one is on the top, one is at the bottom. You have a Br that is in the front. Okay, so you take my white atom as Br. So I have a Br at the back on the left-hand side here and a Br in the front here. Then my hydrogen will be that yellow color ball. The one here is in the front and the one here is at the back. Now what happened is, from the looks of this molecule, by right, it should be able to rotate light because it doesn't have an internal plane of symmetry. However, if you take this bond and you rotate it this way, the molecule becomes symmetrical. So then it is able to rotate light. So by right, if based on what they draw, it should not rotate light. But as long as you can rotate the molecule such that you produce a symmetrical plane, then it will be not able to rotate light anymore. So that's why this one cannot rotate light. Understand? Same thing for 3 lah. 3 is same issue lor. So what happened is now if you see my Br is now in the front here and my Br is now at the back here. So if I rotate, it becomes symmetrical, then it cannot rotate light. So like what you say lah, if let's say technically, so to answer the question on the top at 421, if you rotate the molecule such that it's no longer symmetrical, then yes, it will be able to rotate light. Okay, I think basically that's all the questions